Thank you all for joining us this morning. We have a lot of wonderful presentations and speakers from around the world today, focusing on geophysical innovation regarding munitions and demining. We don't have a surplus of time. If you saw the agenda, it's pretty tight, so we want to be conscious of that. My name is Harry Wagner. I will introduce our first 5 speakers until our short break. And then my co-chair, Jasper Bauer from Columbia University, will introduce the rest of the speakers after the break. Each speaker has 20 minutes. The intent is 5 minutes for questions at the end after their 15-minute presentation, but that might vary a little. Feel free to post questions in the Q&A, and if they don't get answered because we're short on time, we do have a whole hour at the end in order for those to be answered. So with that said, please put who the question is for, so if we don't get to them at the time, at the end of the day, we know which speaker your question was intended for. And with that said, I'll introduce our first speaker here, John Jackson. He's a geophysicist with the Environmental Munitions Center of Expertise for the Army Corps of Engineers. He's worked in the environmental and military munitions field for 20 years, and his focus is on electromagnetic technologies for cleanups. Those led him to being an early adopter for advanced geophysical classification, or AGC, technologies through CERTIP and ESTCP live demonstration sites. From there, Mr. Jackson joined the EMCX, and he became the program manager for the Advanced Geophysical Classification Accreditation Program, or DAGCAP. Outside of that, he enjoys hiking, traveling, breweries, and ultimate frisbee. His presentation is AGC and a few thoughts on where Munitions Response Program is heading. I'll hand it off to you, John.
Thank you, Harry. And as opposed to what Harry just said, this presentation is on nothing innovative, but how the U.S. Department of Defense has made geophysics very boring. So we'll, with that, we'll jump right into it. So I really laughed. If I had not been forced muted yesterday, I would have laughed harder than Jan did when Friedon asked the question about advanced, and Jan had a problem with the word advanced. We had a problem with the word advanced as well. So we had to draw a line in the sand in terms of defining what is advanced geophysical classification. So we did define it. It's multi-axis, multi-coil, electromagnetic induction sensors, and then here's where the key comes in, that have been validated by the Department of Defense Advanced Geophysical Classification Accreditation Program, DAGCAP, which we'll talk about a little bit later. But it's the process by which we're leaving metal that is not explosively hazardous behind in the ground, and we're only going after the metal we care about, which we call targets of interest, or TOI. So we define that pretty clearly, and what's not on this slide, we actually define it as the ability to reduce the clutter digging by 60%. So there's another part of that definition. So Jan, there's your answer for advanced, at least from the US perspective. Had I known what Michelle was going to talk about yesterday, I probably would have reduced a couple of these slides, but we'll rush through it anyway. She did an excellent job covering the EMI portion of Geophysics 101, AGC 101, but just from a different perspective, we have multiple transmitters, we have multiple receiver cubes. So those are the XYZ orthogonal receiver cubes that we're receiving, or multi-component. We've got tons of versions now. I think the first few out of the box all sort of looked like the left-hand side. Those were the Metal Mapper 2x2s, the TEM-senses, TEM-TADs of the world. On the right-hand side, some of the dynamic sensors, one-pass classification sensors, which we'll talk about in a second, took advantage of more receiver cubes, more area, the intent to collect more data faster. This graphic has been around for a while now. It's a number of trainings developed by CERTIP ESTCP, but I really know no better graphic to portray what we're actually doing. So as the munition is in different orientations, depths, different spots below the coils, the responses, the decay responses are changing, and it would be near impossible to attempt to classify these with current models, but we invert them into polarizability curves. So these are the XYZ principal axes directions, and we get nice pretty curves. Little noise at the end, but in general, this is what we're using to do a classification. So this next slide, this is where the meat of the matter is. Does our set of polarizability curves match something we care about? So the computer's doing this, looking at it a little bit closer than we are, but the visual eye can even tell us, is this something we care about? So on the left-hand side is our data from the field. Right-hand side is a horseshoe, piece of frag, muffler. Well, it looks like it's a 37 millimeter. In terms of another definition that DoD went through, there's a lot of thresholds, a lot of criteria that goes into these comparisons, into these library matches. We combined several of the most important ones into one statistic. It's called a decision statistic or decision metric. In general, most of our software ranks that between 0 and 1. So above a 0.9 is a target of interest we might care about and might want to go dig. So that's classification in a nutshell. See Michelle's presentation if you want a little more in depth on that. She did a really good job with that. There's lots of instrumentation now. As I said earlier, we had probably 2 or 3 different versions of the instruments for a few years, but now industry has responded. The hardware vendors have responded, and they're recognizing we've got all sorts of environments we're collecting data in, so we need different platforms, different form factors to help our field crews get the data they need. So in comes DAGCAP, and once again, I laughed at Jan's. I thought my program was a mouthful, but I won't even attempt to say the German program. So that was a little tough for me. So where does this stem from? What's the backbone of why we insisted on DAGCAP? So we have a Department of Defense Environmental Protection Agency Memorandum of Understanding. Look at the date on the bottom right of this box, March 2000. So for over 20 years now, we've basically said, collect as much digital geophysical data as possible, georeference to the maximum extent possible. We want that clear audit trail. We want it to be repeatable, and we've had that in our guidance for over 20 years now. Our own DIRT manual, which is the environmental restoration program, how we conduct business, how we conduct cleanup actions for our program. It basically regurgitated that memorandum of understanding in our own guidance, and then took it one step further, basically said if we're not doing that, we should forward a memorandum to the DoD Component Secretariat. So that's scary. For you Europeans, that's way up the chain. So it's something we haven't done a good job of abiding by until the past 7-ish years. We've gotten a little bit better at that and taken it a little more seriously. So how do we ensure quality? So from my perspective, there's technical needs and administrative needs. The technical needs are obvious. This is what a lot of our presentations are talking about. How do we maximize our coverage metrics? That's where does the sensor itself traverse the ground, and at what density are we collecting that data? We need smart, reproducible parameters, processes for detection and classification, and then from my perspective, probably the most important of those 3, the audit trail. We need to be able to go back to that digital record, understand what the process was, be able to repeat that process, audit it, QC it, QA it, whatever's needed there. There's also administrative needs. So there's the Uniform Federal Policy Quality Assurance Project Plan, UFP-QAP. There's various we call them toolkits or templates for how to do work in different phases, but that's basically our work plan. It has minimum requirements in there. It gives a basic structure of how to do work. Our stakeholders and regulators really like that because they know we're following a process. They know where to look for the information they're looking for. So good there. Then comes in DAGCAP. So as we were coming out of the research side into the production side, it was pretty quickly realized that not every geophysicist was created equal. Not every process was created equal. Not every sensor was created equal. So there needed to be a way to manage those things. So on the personnel side, we had looked at things like professional licensure or certifications, but instead we went with accreditation. So we're accrediting the company. So how does this fit into DoD? Well, I'm the program manager and I don't even understand this chart, but it's a lot of arrows going multiple directions. But we're under DoD. we're part of what's called the Environmental Data Quality Work Group. In that work group, Navy is the lead service. So my unofficial boss on that side works for the Navy. He's the chair of EDQW. But Army and Air Force have the component principals on there, and then there's technical representatives and subject matter experts as part of that as well. There's also external organizations, with the primary one being Intergovernmental Data Quality Task Force, or IDQTF. And this is where the EPA comes in. So we've got EPA as part of that. We've got the states, and then we've got all the DoD principals and their subject matter experts. So they're the ones that work collaboratively to address the environmental issues of emerging concern at federal facilities, promote implementation of consistent and transparent intergovernmental quality systems, and ensure a scientific basis for environmental decision making. So big task considering all of our various hazards out there. But per the subject matter of this summit, DoD created this DAGCAP program. It was stood up in 2016 and then put in place where that if you are performing AGC on a site, thou shalt be accredited. Your company needs to be accredited. So that started January 1st, 2017. We're compliant with ISO 1725, the 2017 version, which that was, as when I came on board for the program, first big update we did was 2005 to 2017. A lot of excitement there. It establishes some personnel skill requirements, but puts the onus on the company. The company we call a geophysical classification organization, so it's their responsibility to ensure their personnel are trained. And then it established some reporting requirements for QA failures. In terms of components of DAGCAP, we have an initial accreditation. So we now have 15 GCOs that have been accredited. It's a decent mix of small and unrestricted companies. So for those of us concerned with how we contract things, we've got access to all sorts. There's an initial assessment of the quality system, so that's performed by the accrediting body, and then there is a actual field test at Aberdeen Proving Grounds, and it's pass-fail. You have to get 100% correct classification of the target of interest or our inert munitions that are there, and as I said earlier, the 60% rejection of clutter, and it's just pass-fail. So then we have a biennial reaccreditation. So the initial plan was to actually bring back each GCO to Aberdeen and do the test. And it turned out we didn't see a lot of failures in the field. The failures we saw were either in following SOPs, decision-making, processing, that sort of thing. So we actually developed a synthetic site test. So we have synthetic AGC data, and that's the assessment performed every other year. What I was excited about is the failure rate on the synthetic site mirrored the one at Aberdeen fairly closely. So I view that as a good thing. It's a legit test. We manage the DoD AGC library. So those are the set of polarizability curves of things we care about. It is just a subset. We're constantly wanting to add to that. We're performing our first major update, hopefully this year, thus the question marks. And then there's hardware and software validation. So the hardware mirrors the Aberdeen Proving Ground test. Same sort of concept where they show up and demonstrate their equipment can achieve the 100% classification and the rejection. And then there's software validation, which is the results-based. And that's what we're focusing on, sort of transferring the responsibility from DoD to the software vendors. They're a little more equipped than we are to do the full validation test. We operate under the Quality System Requirements 2.0. So just an overview of what that is. This is the document that sort of adjusts our compliance with ISO 17025 2017. There's a lot of chemistry-like language in there, which I know drives me up the wall and drives a lot of my fellow geophysicists up the wall. But the way we view it is our GCOs are the labs doing the testing and calibration in the field. So that's why you see a lot of the chemistry sampling type language. There's multiple parts. The main part is what provides the overview, the general structure, resource process management, and the whatever we need to modify from 17025. Appendix A has an adaptation of our QAP worksheet 22. These are what you would typically think of our QC requirements. It's similar to what you would expect for production, but it's what we expect you to demonstrate while at Aberdeen. So it's a slight different change on what our thoughts are. Appendix B is the more interested one. We actually put the onus on seeding. And if there is a missed, we call QA seeds validation seeds. So these are the seeds the government puts in to test the system as you're collecting data. If you miss one, we view that as critical enough that we implement a QA stand down. So the company stops work until we perform the root cause analysis and figure out what the corrective action should be. So just a quick overview of some lessons learned and what we're doing moving forward. I could probably spend a whole day on each one of these, but quick overview. We have recently realized the quality we're getting from AGC instrumentation far exceeds what we've been doing in the past. So as we move from remedial investigations, which is the characterization of the site, to remedial actions, which is the cleanup of the site, we realize that our density estimates coming from those RIs don't correlate that well to what we're seeing in the real world. So we're dealing with that now program-wide. We have a mechanism called remedial design where we can go out and collect more field work. So we're using that mechanism quite frequently to figure out what are the true anomaly densities. So on the top right, that comparison is one of the worst cases I've personally seen. We had an EM61 estimate of 29,000 total targets in this particular area. Metal Mapper 2's transects had 218,000 estimated targets, and the actual, and that was extrapolated. We have not dug that whole area, but a sampling. The extrapolation of what we're actually finding is 223. So we've got an order of magnitude difference between those two estimates, and that can be a concern when we're talking millions of dollars for cleanup. Are we talking millions or hundreds of millions? We also have time-critical removal actions. So those are where we saw an imminent hazard and came in and cleaned it up as fast as possible. A lot of those were done with analog technologies, which do not have 100% probability of detection, as tested repeatedly throughout our test sites. But on top of that, it was usually for that imminent hazard. So it might have been just for the top 6 inches. It might have just been for the surface. And that's probably the bigger problem there. We know we left stuff behind. So we've quickly learned we shouldn't just depend on that. We need to go back and characterize that to make sure we are, the risk-based scenario that we have for that particular site is as we thought it was. Some of our sites are still using EM61 for its speed to detect anomalies and then following up with Q to AGC. That's fine, but it does implement some problems. The footprint of, or the size of the transmitter and receiver, and then the footprint of that anomaly causes some problems. So you need a robust target selection method to cover the entire anomaly footprint and to account for the dig radius. So some of our more recent guidance is attempting to address that. But we've seen, like in this image, we've had to put 10 targets on that to make sure we go back and queue the entire footprint of that anomaly. For root cause analysis, we're recognizing oftentimes contractors did not get to the root cause or have corrective actions that prevent the issue from recurring. This is a big focus for the program now. I'd say as a general trend, we have seen huge improvement. I'm really impressed, but there's always room for more improvement. And the whole program gets better when we learn those lessons. And then my personal cry for help, we need better processes, algorithms, and or models for our multi-source scenario. So that means multiple pieces of metal underneath that same footprint of the instrument and what we call saturated response areas. So there's so much metal in an area that you can't select individual targets or classify individual sources. So I believe this is a critical need, and developing tools to help us manage that is paramount to moving forward. Just a quick cost savings slide. I don't want to spend a lot of time on this, but I do want to point out we have, as advertised, AGC is saving us money. So I personally, I love the higher data quality, but we are seeing cost savings on our projects. So this is just a comparison. The left column is 19 million for this particular site. Had we gone out and detected everything, dug everything, if we had gone out, detected and queued, it would have been about 11 million. If we had gone out, performed what we call informed source selection and queued, it would have been 7.8. And if we had just done one pass dynamic classification, it would have been 5.8. These are real numbers I'm seeing. So if you don't trust those, because we contract things as firm fixed price, which may not mean something to those of you, but transfers a lot of risk to the contractor in our world. We also do cost reimbursable contracts, and I have a few examples, and we're seeing similar cost savings. We're seeing about 35 to 45% there.
Hey, John, you got 1 minute.
Thank you. Better comparison there. Finally, we're realizing that using AGC to estimate sizes is a huge benefit for us in the US. The exclusion zone when we're digging on a munition is based on the hazard fragmentation distance, and we default to the worst case scenario. But by using AGC and estimating size, we can establish a flexible zone. So I'm going to say we have some easy sites where we've demonstrated 1.8 million in cost savings and evacuation costs and digging costs. For harder sites, I'm going to point you to the next presentation. It's a little more complicated. So my closing thoughts, AGC has undoubtedly led to higher quality data. We're continuing to see cost savings in our cleanup program. I'd like to see some improvements in our processing and models assessing complex source scenarios and saturated response areas. I'm very proud of all our contractors using all of the tools in the toolbox. All of our sites have multiple methods on them to help us fully clean up that site, which is good. And most of our projects are attempting to utilize AGC to the maximum extent possible, which is great. And finally, we'll end on a slide less boring than geophysics.
Thanks, John. We didn't have time for questions here, but we'll circle back and we will do those at the end. You kind of gave us our segue for our next presentation here, which is from Craig Murray from Parsons and Stephen Brown from HGL. They are discussing exclusion zones in their presentation that we'll let them get started now.
Perfect. Thank you for the introduction. My name is Stephen Brown. I'll be co-presenting with Craig Murray from Parsons. Today's slide deck is about using AGC to reduce evacuations. Next slide, please. All right, so using AGC to reduce evacuations, we're going to talk about standard evacuation requirements, reducing exclusion zones based on AGC size estimates, estimating munition size using AGC, Waikoloa project overview and AGC size categories, examples of exclusion zone reduction, accuracy of size estimates, future improvements to further reduce need for evacuations. All right, so standard evacuation requirements. During this, all non-essential personnel must be evacuated within the maximum frag radius for the munition response site being worked. Example, landowners and the public need to be evacuated. Advanced coordination is necessary to ensure residents can and will evacuate. Often this requires door-to-door visits to ensure that folks do evacuate. The UXO safety officer confirms evacuation of all non-essential personnel prior to intrusive operations beginning. So the onus is on the contractor to ensure that our exclusion zone is set. An intrusive team comprised of 7 or less unexploded ordnance techs are led by UXO Tech 3 to investigate subsurface items identified in advanced geophysical classification data collection activities. Reduce exclusion zones based on AGC size estimates. The identified digs are divided into their estimated size category by munition type, and the relative EZ is applied. Coordination efforts are conducted to evacuate all non-essential personnel within the respective EZ for the munition size category being intrusively investigated. If applicable, additional engineering controls can be applied to further reduce EZs. Example here is an MOFB, pictured to the right. If using additional engineering controls, ensure the suspected munition explosive of concern within the size category being applied is approved for mitigation purposes in accordance with the associated manual. All right, prerequisite process to employ reducing exclusion zones based on AGC size estimates. In accordance with the Department of Army Technical Memorandum dated May 3rd, 2022, the amendment of the project-specific ESS or ESPs required. Standard operating procedure must be developed. The GCO must develop a standard operating procedure for evaluating and documenting the procedures to be used to determine the munition and MSD to be used in place of DDSP MGFD. An accredited DADCAP GCO must collect data. The DADCAP must have validated technology, example, hardware, and validated instrumentation used to collect AGC data and software used to process the AGC data. Both the MR and AGC QOP require 100% correct size predictions. If a large item is found at a small source location, a root cause analysis and corrective action must be completed, and the MSD may not be reduced based on TOI predictions until both DADCAP and the Military Service Explosive Safety Office has reviewed the RCA and approved the CA to be taken. All right, so at this point, I'm going to turn it over to my co-presenter, Mr. Craig Murray. Craig?
Thanks, Stephen. First slide here is going over the AGC process that I think has been gone over by a few folks, so I'm going to speed through this one. You're probably all familiar with the standard time domain electromagnetic induction sensor that has a single transmitter and receiver. Yeah, I think we're using the same example figure here as that John did. So these are the polarizability curves, the intrinsic properties of the object. Compare it to a library, and we get what I'm calling a match metric. John was referring to that as a decision statistic. So going beyond just doing the classification with the AGC data, we're trying to estimate size. And so there are a couple of ways to do that, a couple of options that we considered. The first would be to use a numerical size estimate that would be based on the early time gates in the polarizability curves. So either just the primary one or the combination between the primary and the secondary and tertiary. And some software does scale that numeric measurement to match up with the munition diameter in decimeters. We actually used option 2, where we used the best library match item to put in the size estimate. So if the polarizability curves best match to a hand grenade that was in our small size bin, then we would, estimate the size of that source as small. If it was a medium item, it would be in a different bin. If it was a large item, it would be in the large bin. We did have a few special cases I want to hit on quickly. First of all is inconclusive results. We do have kind of an industry standard of requiring a fit between measured and modeled data of at least 0.8 on a scale from 0 to 1 in order to use that data for making decisions about things like whether to dig it or not. And we're also using that same threshold of quality requirement in order to estimate size. So in this case that I'm showing here, there's the fit coherence, or the fit between the model and the measured data was below 0.8. And so we used the most conservative size bin, the largest size bin for this inconclusive location. Turned out we found a piece of rebar nearby that was not large, but it's better to be digging something with more of an evacuation than less. Other case that I want to go over is very closely spaced sources. So in this case, we have 2 sources that are very close to each other. One was a shallow Mark II grenade match with a higher match metric, and then the other one was a deep 81 millimeter mortar with a lower quality match metric. Even though the small item was the better match metric, it looked more like what was in our library. We used the large size category for this dig because it was possible there was an 81 millimeter mortar there. Turned out there wasn't. It was 2 pieces of scrap metal at this location. So moving on to the specific project we're working on, this is one of the RDs, or remedial designs, that John mentioned. The Waikolo maneuver area is the overall site. It's on the island of Hawaii, and as all of you know, that's a volcanic island, and so that makes the geophysics pretty challenging. Focusing on the small neighborhood that's close to town in the site, and you see that there's a lot of small parcels with houses on them. They're all about 1/4 acre in size, so 30 meters by 30 meters roughly. The green shaded area on here are the work areas that we're operating in. For the geophysics part of the site, this project, we use the Apex advanced classification sensor. It's got 3 transmitters, 6 receiver cubes that are in 3 axes, uses the 8 millisecond decay time. For classification, we used a threshold of 0.85 on a scale of 0 to 1. And we were looking for the smallest type of object we were looking for here was a 37mm projectile down to a depth of 0.25 meters, which may not sound all that challenging for folks working in benign geophysical conditions, but on a volcanic island, it can get pretty challenging. For the size estimates, we split it up into two different bins, a small bin and a large bin. And we drew that line where we had a gap between the size of munitions, and that was pretty much between 60mm mortar size and 81mm mortar size. One advantage of that, using that that point for drawing the line between the two categories, is that the MOFB that Stephen talked about earlier, it is only rated to be used for items that are up to 60mm mortars. So we could use the MOFB for small category sources, but not for large ones. And that helped to reduce the evacuations even more, as Stephen's about to go into in more detail.
Thanks, Craig. So we're going to cover some examples of exclusion zone reduction without additional engineering controls. So as you guys can see in the illustration to the right, the yellow arc depicts a maximum EZ for the MRS, which is based on 81mm. Please note that 81mm is a high capacity 81mm. It's not the teardrop shape, so its NEW is a little bit higher. The purple arc depicts the EZ for small category targets. It's based on 60mm mortars. A pictured approximate 40% reduction in homeowners required to be evacuated by employing the small size category or small bin thresholds. 3,256 targets were categorized as small, which we employ the purple EZ arc, which equates to approximately 8 homeowners per dig not being evacuated by employing the approach pictured. All right, so we're going to talk about examples of EZ reduction using the MOFB as an additional engineering control. Again, the yellow arc depicts the maximum EZ for the MRS. The purple arc depicts the small category arc based on 60mm mortar again. But now we're going to add the orange arc, which is depicting an EZ that's utilizing the MOFB, and it's based on the top end of the small size bin, which is a 60mm mark. And then the red arc depicts the EZ for the open front of the MOFB. As you guys can kind of see in the bottom right of the illustration, there's an open front where the team would have access, which we'll show in a later slide. Excuse me. Pictured is approximately an 85% reduction in homeowners required to be evacuated by employing the MOFB, an additional engineering control methodology. Utilizing the MOFB to further reduce exclusion zones for the 3,256 small categorized targets equates to approximately 12 homeowners per dig not being evacuated by employing the approach pictured. So as promised, here's an example of intrusive investigation utilizing the MOFB. So you guys get a really good picture here of a team digging down on their hands and knees inside there. That box is centered over a target of interest. Team members are intrusively investigated buried metallic items while utilizing the MOFB inside a densely populated neighborhood, which Craig gave an overview in a previous slide. Using AGC EZ reduction for this project area reduced mandatory evacuations of non-essential personnel by approximately 50% or 7 households per dig. That's pretty significant. Using additional engineering controls in the form of the MOFB limited mandatory evacuations by approximately 85%. So that's another 13 households per dig. All right, so back to you, Craig. Thank you.
All right, thanks. So we've done all these investigations, so evaluating the results and seeing how we did with size estimates. We made estimates for almost 5,000 digs, and about a third of them were categorized as large and 2/3 as small. I think that's a much larger percentage as large than would happen on a site without all the geologic concerns. Of those large source estimates, almost over 1,000 were inconclusive sources. So ones that we weren't confident about making a decision whether they were large or small. Intrusive results there, we found 9 pieces of MD at the large source estimates. All those were either at inconclusive source locations or at locations where we had 2 different sources, one small and one large. For the small sources, we found 22 MD and 1 UXO. I'll go into a little more detail with examples of the large estimate source. This was a source that we intrusively investigated. The estimated depth of this is pretty deep for the type of rocky soil we're in. So we were really expecting this to not be a munition, and we investigated it, and it was just a geologic response at this location. That's the one in the center here, the 2426. Small size estimates. The largest items that we found at the small estimated sources are pictured here. One example is the piece of pipe that's up in the upper right-hand corner of the slide. That one's about the same diameter as a 2.36-inch bazooka rocket, fairly long as well. It's a pretty good match with the polarizability curves to the library. While it was near the boundary of the small to large bins, it was an accurate estimate, and so we're confident that that we made the right decision there. And then the other example, the other largest item is more plate-like, as you can see in the polarizability curves here. And this again was near that boundary between small and large, but we think we made the right decision again to categorize it as small because it was closer to the size of a medium ISO, which is a 2-inch diameter piece of pipe. And then the one UXO that was found was categorized as small, and it was a hand grenade, so clearly falls in that small size category. The one item that I want to talk about a little more, it kind of stopped us as we were doing this reduced evacuation procedure, and that was a 75 millimeter projectile cap. You can see the photo on the right there, and the diameter of that is 75 millimeters, so it's larger than the 60 millimeter size that we were calling the top of our small bin, and this source was categorized as a hand grenade at 17 centimeter depth, which is pretty close to the depth that we actually found it at 15. And we stopped using the reduced evacuation procedures, gathered the geophysicist and some of the UXO experts on the site, and discussed these results and determined that the actual cap, because it's so short, it's more spherical in size. It's similar size and shape to a hand grenade, so it makes sense that it was categorized that way. We decided that everything was working as it should, and we could resume using the reduced evacuation zones. But we took the time to consider that when finding something that had a diameter above 60 millimeters. So we've considered a few possible improvements to further reduce the number of evacuations that are required. First is changing to a size threshold. So instead of using option 2 of using the best match to put it in a size bin, to use a numeric value. But because we found a couple of items in the small bin that were close to the boundary, we decided that we're not going to make any changes there. We want to make sure that we're not going over and making the critical mistake of putting a large item into the small category. And co-located sources was another thing that I talked about earlier. We considered leaving some of those multiple source situations in the small category, but there really is a possibility that there's 2 different items at that same location, so we decided not to make that change either. And then inconclusive digs, that is where we identified as a place where we could make improvements. Those make up 65% of the large category sources. We could do additional analysis of those inconclusive digs, possibly collect queued AGC data, which has a higher signal to noise ratio. And taking a different approach, we may, instead of getting an inconclusive result, get a conclusive result that would allow us to either take it off the dig list entirely or categorize it as a small dig instead of a large dig. So that's what we're looking at for the future. I'd like to acknowledge co-authors, Stephen, who is trading off with me today, and then Richard Perry and John Jackson from the U.S. Army Corps of Engineers. U.S. Army Corps of Engineers was managing the project I mentioned, the Honolulu District and the Huntsville District, and then the prime contractors for that project were HGL, and the Geophysics subcontractor, or GCO in DAGTAC speak, was Parsons. So if anyone has questions, if we have time.
Not right now, but at the end of the day, we'll have some. Thank you.
Excellent job. Thank you both. And perfect job on timing as well. So that moves on to our next presentation here. And I should have opened by saying I apologize in advance for anyone's names who I butcher today, like our next speaker, Florent Collin from MAPPEM, MapBM Geophysics. He has a background in seismic data actually, but switched to EM 3 years ago. And he is a research engineer focusing on data acquisition, processing, and applied research. His presentation is detection and location of ferrous and non-ferrous metallic UXO by an active EM system.
Yeah, thank you, Harry, for the introduction. The name pronunciation was close enough. So yeah, as you said, I'll be presenting ferrous and non-ferrous detection in marine environment using an active EM system. Object detection in marine environment mostly concern project de-risking, archaeology, also general depollution, obviously, and that in Europe at least would mainly concern marine renewable energies, which is booming right now. Cable laying, cable detection, and the cable industry in general, and also various defense applications such as marine warfare. In this presentation, I'll be focusing on metallic ferrous and non-ferrous objects. There are other types of ammunitions and other type of objects like wood, fiberglass, and all that. I won't be talking about those today. There are several instruments that are used to detect UXO in marine environment. So that goes from multi-beam echo sensors that scan sonar, but these will only work for non-buried objects, so these that are on the seabed. A commonly used instrument is also magnetometer, but that obviously will only work for magnetic materials, so mainly ferrous materials, and can give a lot of false positives. And another technique is sub-bottom profiler, which is not always the most reliable to actually detect targets. The system I'm presenting is called the MapBM 3D. It can detect metallic ferrous and non-ferrous objects, whether they're buried or not, and has a good localization capabilities when it's used with ultra-short baseline USBL. So it's a perfect complement with all the techniques. None of the techniques that I just mentioned can work on their own, and they all have to be used in conjunction to give the best results and the best the best results on an area. Very simply, how the system works is that we inject current in the environment, and we measure the response from the object, and then through data processing and interpretation, we get a localization for that object. A quick description of the system. So it's composed of two fishes that you can see here to the right. The main one to the right, to the very right, includes all the acquisition electronic that is stored, and so the whole system is stored close from the seafloor. So the two fishes carry the injection electrodes. They are located just underneath there. And so these are the ones that are in charge of injecting current in the environment. So roughly around 50 to 60 amps, depending on the local conditions. And we are injecting 3 times per second. After these two fishes are the measuring cable, which carry the measurement electrodes. So we have between 6 and 8 electrodes per cable. And the 3 cables are used to increase the swath of the system, so to optimize for survey time. Along with the system is the acquisition software, which allows real-time control and navigation of the system, since it's stored close from the seafloor, so between 1 to 3 meter altitude. It's important to have a real-time status. We also have real-time data preprocessing, which are the 3 colored panels that you see in the top right in orange. And you can see actually a detection on the screen in the middle. Moving on to some examples. I'll just show a quick example of some telegraphic cables before moving on to UXOs. So this example concerns all telegraphic cables from the late 19th centuries, I believe. The cables are rather small. You have a picture on the bottom right. Their diameter is below 10 centimeters, so it's quite small. And so for this cable, we have the theoretical cable positions, so shown in red on the map here. So we drew survey lines that are more or less perpendicular to these theoretical positions, and so we got several hits that are seen on either side of the map. So the detection of the cable is rather clear here and allowed us to locate the cable. So each of the green dots that you can see on the map are actual detection of the cables, and so we can see that those detected position do not really match with the theoretical cable positions, which makes sense because these positions are usually quite rough, especially for such old cables. Moving on to UXO. So here it's an example of an LMB detection. So LMB are Luftmine type B, which are German bombs from World War II. And these are quite big bombs. I think the size is roughly 2 meters long and 60 to 80 centimeters in diameter, and their casing is in aluminium. They have a few ferrous parts, but not so much, which make them almost invisible to magnetometer. So MAPM had the opportunity to acquire data on top of an actual LMB. That LMB was detected through bathymetric data, so it was just laying on the seabed. And so the equipment was acquiring other data nearby. So we had the chance to go acquire data on an actual target. So we can see that the detection are again quite clear on either side of the map here, with these red V's, we call them, like the letter V. Unfortunately for that survey, the localization is not so good. Water depth was quite deep, and we did not have USBL localization, so it was all done using layback, which is not great for object localization, for precise object localization. But nonetheless, the detections are really good and show that like a ground truth of the system for this type of bombs, which are a real problem in the channel here in Europe. Next up is a surrogate item for an LMB. So that's an aluminum target that is inert. It's a fake bomb basically. So it's just a hollow aluminum cylinder that's 2 meter in length and 60 centimeter in diameter. Basically, it is this fake target is used to assess the equipment capabilities before an actual survey. So we drop the target on the seabed and we run line on top of it, survey lines on top of it, and then we process the data to show the good working of our system. So for this example, the target of the location of the site is here in the middle of the map, so the red dot, and so we ran several lines from southwest to northeast. Again, the detections are shown on either side of the map. So again, very clear detections. These lines were acquired at various altitude above the object. And so we ran over the years. We ran several of these SIT survey. So all of them on top of this fake target. And so all of them prior to actual commercial surveys. But these SIT survey are really great because we have all the information we need in terms of object size, object localization, distance between the object and the detection system, which allows us to make this kind of sort of plots of figures. So what we have here with the vertical axis is just depth, and horizontal axis is the cross distance between the object and the survey equipment, the system. So with this diagram, the system is located at 0, 0 here at the top in the center, and so all the detection are shown relative to that. So either for any of the three streamers, so with the different colors. So obviously, what we can see is that we have the amplitude of the detection that decrease with distance, which is quite an obvious remark. And basically, we have quite a few detection up to a 6 meter radius, and then some up to 7 meters, and less so after 8 meters. And so we from these results, we assess that the detection range of the MapM3D system for this type of object is between 6 to 7 meters. That will obviously depend on conditions and depend on survey conditions. The MapM3D system allows for good localization of an object in the X and Y sense, so in the horizontal plan. But what about the depth of the object? It's a common and difficult problem in the industry, which is the depth of burial. That can make an object a target of interest for an operation, or can make it too deep to be interesting, or to be a real risk for operation. To assess that question, what we did is that we took one of the survey lines above the surrogate item that I just mentioned. So what you see here is a map of bathymetry, and you have the surrogate item that is visible here in the middle of the map. So we consider the one survey line that's crossing on top of the object. It's approximately 2 meters above the target, so quite close, which is also very nice signature. And so the survey line is slightly off to the side, meaning that the central cable will be a little bit off to the side of the object, well, not crossing straight through, not in the middle. And that means that the right cable will be just off to the side of the object. So we can see that on the data, which are shown here. So on those data, each of the line for the left plot and each of the pixel line for the right plot corresponds to one measurement dipole. So we have between 5 and 7 per cable, which correspond to 6 to 8 electrodes, as I mentioned before. And so we can see that, for example, the right cable, which is the bottom one, will have a lower amplitude because it's not directly on top of the object, as I said. So that's our starting point. These data are our starting point. And so from that, we're going to try to model this object. So we are doing frequency domain modeling. It's based on the integral equation model. So we are modeling 21 frequencies, and then we are converting those to time domain to apply our in-house processing. And so we're modeling for induction and IP effects. Here's the setup of the model. So basically, we have 2 cubes that are 1 meter in size, so that makes for a 2 meter by 1 by 1 object. And so we have a system that's crossing through that object slightly off to the side, just like the real survey line. If I sketch that a bit more, you have here the 3 measurement cable, which are not represented entirely, but it's just for the image. And so you have the port cable here at the top that crosses through the object, the central cable just on the side, and then the starboard cable that is off to the side of the object. And so we are modeling 2 meters above 2 meters altitude above the object, just like the real survey line. From that modeling, we get the following data. So these are the model data, and I'll move on straight to the comparison. So to the right are the actual data that I presented before, and to the left is the model that I just showed. So we can see that we have a great fit between the two of them. This is not inversion yet, it's just handpicked parameters to match the two, but we can see that with rough unpicked parameters, we already have great results. Now, the next step we are doing before moving on to actual inversion is kind of a sanity check to see if that's something that we can actually do. So it's basically a brute force grid search. We are basically modeling a lot of different parameters, so different altitudes, different cross distances, different object size. and just doing cross correlation on those between our actual data and the various models. So the 5 panels you can see here are for 5 different model object sizes, with depth being vertical axis and cross distance between being the horizontal axis. The best fit for this example is the last one at the bottom. So you can see that you have the actual object location that is shown in blue in the middle, and the retrieved location that is shown in white. So these two are quite correlated, quite well like at the same location. However, in terms of object size, it's not perfect because the object at the bottom has a size of 2 meter by 2 meter by 1 meter. Whereas our original object was 2 meter by 1 meter by 1 meter, so slightly smaller. So still some improvement in terms of the size volume, but a first great step for depth estimation with this example. So as I said, it's just sort of a sanity check before going full force into inversion. So hopefully with the inversion, we obtain accurate depth of burial for the target and the volume of the object. And so eventually we'll have also to inverse multiple lines at once. That's quite challenging in terms of computation, basically. If you only inverse one line, you can do sort of 2D models, but inversing multiple lines, you'll have to do 3D, which is quite computationally intensive, but will give obviously much better constraint. Some takeaway here. So that system allows for metallic ferrous and non-ferrous items. So that's aluminium mainly. We can precisely position the targets in X and Y. And then there's still some work needed to give an accurate depth of burial and object volume, and we also have a high sensitivity of the volume to the IP coefficients. Thank you very much.
Thank you. And we do have a few minutes for questions. We had a couple questions here. One question: what is the optimal altitude of the system above the seafloor, and how is that maintained?
So I don't know if there is really an optimal altitude. The main constraint is that usually we have a depth target. So let's say 3 meters below seafloor. And so if the detection range of the system is 6 meters, for example, we won't fly above 3 meter altitude, just to put it simply. Sorry, what was the second part of the question?
How is the altitude above the seafloor maintained?
So the system is stored with a winch that's installed on the boat, so you can see it on the picture here at the very bottom, with the red motor here, the red engine. So it's basically just winding and unwinding the winch that controls the depth of the system. So it's really controlled by the operator.
Okay. And another question: what is the maximum depth that the system can be used at? Do you think it would work for the deep sea?
The system as is not set up for deep sea. I think the aluminum body of the system, which is the white part that you can see on the picture here, is rated for 200 meters, I believe. More realistically, we've done surveys down to 50, 60 meters water depth. After that, you have constraints in terms of drag, notably for the cable. But there are systems that are really that exist, deep towed systems that exist that can go down to 6,000 meters. So this system as if is not capable of that, but it's definitely doable with some adjustment and some like titanium housing and stuff like that. Yeah.
Okay, thank you. We do have one more minute, so we have a couple more questions here. Is this system, you mentioned frequency domain, right? Or is it DC resistivity, or both?
So we measure everything in time domain. We do DC resistivity with it, okay. And so we also measure the time response here. The frequency is only for modeling.
Okay, thank you.
Thanks.
And does the minimum size or maximum depth of the sensor can see change between ferrous and non-ferrous objects?
So ferrous and non-ferrous will be a matter of the response from the target. So that really depend on the actual detection of the object. In terms of size of the object, can go down. We've measured objects that were quite small. We're usually more sensitive to the volume of the object rather than its actual size, so that makes kind of a difference. Okay. Yeah, and so depth, yeah, depends on the altitude. Usually 3-4 meters burial, depth of burial, which is usually enough.
Sure. Great. Wonderful questions, and thanks for all the responses.
Yeah, thank you for the questions.
For being mindful of time. Moving on, our next presenter is Randall Reynolds from Dartmouth College and the U.S. Army ERDC Cold Regions Research and Engineering Laboratory. Randall works there with EMI sensors and is pursuing his PhD in electrical engineering at Dartmouth College. He specializes in developing EMI sensors for remote sensing, for applications such as UXO, IEDs, permafrost, voids, and utilities. His presentation is ultralight, high-frequency EMI systems for detecting explosive remnants of war.
All right. Well, thank you for the introduction. I really appreciate it. As mentioned, my name is Randall Reynolds. I work as an electronics engineer at the Cold Region Research and Engineering Laboratory, where I work with Michelle Maxon, Dr. Ben Barros, and I'm also a graduate student at Dartmouth College with Dr. Friedon Shubdice and Michelle Maxon. And I'd like to present the topic of ultralight, high-frequency electromagnetic induction system for detecting explosive remnants of war. This is a sensor we've been developing in-house at CREL in Dartmouth with the expertise of Michelle, Ben, Friedon. And so I'm going to start with some of the current challenges. So there's been, as we've seen the past couple of days, there's been great progress in detection using current methods. For instance, UXO, there's been great detection and processing, classifying and discriminating UXO from clutter to reduce time and cost radiation. However, landmines and improvised explosive devices, or IEDs, are still present danger to civilians in the military. These explosive remnants of war vary in design, material, size, and the combinations of which complicate detection and can elude current sensing methods. They can be constructed from a variety of materials, such as carbon rods, small metallic components less than 10 grams, wood, short wires, rubber, and you can see some examples in the images on the slide. But the diversity of these materials, their size, conductivity greatly complicates the detection and the classification of these explosive remnants of war. And currently, there's not one sensor well suited for detection of all the materials. So what are the current detection methods and technologies? So there's advanced EMI, magnetometers, ground penetrating radar. These are all great tools for detection and classification, but they all have their limitations. So advanced EMI has greatly improved in the past 10 years. They can classify and discriminate UXO from clutter with very high confidence, but they struggle with low metal content and intermediate conductive objects. Magnetometers have progressed rapidly as well. There are new mini mags, magnetometers with sensitivities of picotesla per root hertz, and they can output 1,000 data samples a second. But magnetometers are limited because they can only detect ferrous materials. And then explosive remnants of war, such as IEDs and landmines, may not necessarily contain ferrous materials. Ground penetrating radar is better suited to detect a wide range of materials. It can find metals, dielectrics covering all the components of landmines, IEDs, UXO, and other explosive remnants of war. But due to high sensitivity and interference from environmental signals, there's a high false alarm rate. Just the point I'd like to prove is that there is no sensor capable of reliably detecting and classifying, all explosive remnants of war, specifically IEDs and landmines. Our group has been working on an EMI sensor capable of detecting and classifying the wide spectrum of objects found in landmines, IEDs, and other explosive remnants of war. So as I mentioned, we have an EMI sensor, so I'm going to do a short EMI background. EMI stands for electromagnetic induction. It uses a primary field to excite eddy currents inside conducting objects or media. This primary field frequency ranges from tens of hertz to tens of kilohertz for traditional EMI sensors. At lower frequencies, the EMI field penetrates the target and produces surface and volume currents. At high frequencies, the currents shift towards the surface. These eddy currents produce a secondary alternating magnetic field that is out of phase with the primary field, and it's this secondary field that can be measured with a coil. There are two types of EMI sensors, time domain, frequency domain. Ours is frequency domain, so I'm only going to talk about frequency domain, but the alternating primary field is always present. So in order to make measurements, we need to remove the primary field, and this can be done geometrically. And our group has utilized a double O or overlapping O configuration to remove the primary field from our measurements. But once received, once the signal is received, it's demodulated into in phase with the primary field or in phase and out of phase with the primary field or quadrature. And so these in phase and quadrature EMI responses vary with size, conductivity, object shape, and material. So I'd just like to emphasize that the INQ or in phase and quadrature curves will change with, explosive remnants of war. So on the right, you can see 3 simulator responses for 3 identical targets, same size, shape, only the conductivity varies. And as the conductivity decreases, the response shifts higher in frequency. And then in this response, you're going to see a linear region followed by a quadrature peak and followed by an inductive limit. And then also note that the size of the material also makes, can also affect these responses. So a small piece of metal will shift higher in frequency. And then, but all these reasons justify the need to move to a higher frequency for EMI sensors, which approximately 100 kilohertz to 10 megahertz to detect and classify all the components of explosive remnants of war. And so what is an IED? IEDs contain 5 components: an activator, fuse, container, explosive, and a power source. Containers can be constructed from rubber, wood, and other low to non-conductive materials. They're triggered by pressure plates, and these pressure plates contain carbon rods, tripwires, and other intermediate conductive objects or small metallic objects. But most of the listed components are low conductivity or non-conductive. And then of the metallic components, most of them are contain small metal objects, such as short wires. And these objects do not produce like EMI signals at lower frequencies due to their size. But all of these components produce EMI signals at higher frequencies than the traditional EMI range. So expanding into the high frequency EMI band will allow for the detection and classification of IEDs and landmines. So here I present our sensor. It's a frequency domain sensor that we refer to as high frequency electromagnetic induction, or HFEMI for short. It operates between traditional EMI and GPR, so 100 kilohertz to 10 megahertz. It uses an overlapping O configuration to remove the primary field. An FPGA provides transmitter signals, and the transmitter board provides up to 1 amp of current. Custom amplifiers apply gain to the incoming receiver coil signal, and then the FPGA demodulates the signal into in-phase and quadrature components. An onboard computer displays the in-phase and quadrature data and logs the data as well. So in real time, the user can analyze in-phase and quadrature curves to find anomalies, and then that can be contributed to explosive remnants of war. Afterwards, the data can be used to, detect and classify, components used in landmines and IEDs. So small metal objects, intermediate conducting objects such as carbon rods, short wires, not conductive ones. So here I present a direct comparison between advanced EMI and HFEMI using a Russian butterfly mine. A Russian butterfly mine, which can be seen in both the photos, is a small, mostly plastic mine with a small amount of metal. On the left, I've included data from HFEMI, a spectrum plot of a Russian butterfly mine at 5 centimeters standoff. It shows a clear broadband flat response in the in-phase data, which is characteristic of a metal response. On the right, I have several decay curves from an advanced EMI sensor, Ulemma handheld, which Michelle presented on yesterday. In this data set, I collected data with the mine at 3 standoffs, 0 inches, 3 inches, and 5 inches. Ulemma handheld was only able to detect the Russian butterfly mine at 0-inch standoff. So HFEMI was able to provide a greater depth detection than the advanced EMI system for this small metallic target. And it shows how great of a tool HFEMI could be in addition to the current sensing methods we have today. And on the bottom left, we collected gridded data with HFEMI. So on the bottom left we collected a grid of data. So on the bottom left is a grid showing the antenna pattern, or sort of shows that the entire array is able to detect. So showing the sensor footprint. And then last year, we were able to collect some in-field data at Fort AP Hill. All data was collected using HFEMI in handheld fashion. So above, I have an image of a 20-gallon ammonium nitrate jug at 4-inch depth. There is no metal in this target. And on the right, I have the EMI responses. In green is the in-phase and quadro response from an area void of any EMI targets. These will be present in all the results. And the red is the in-phase, the red is the quadro response, and blue is the in-phase response. In the EM data, you can clearly see a void response. But what is this void response? Our system operates in the frequency domain, in the frequency range where soil can generate an EMI response. We remove this soil response using a background. So if there is no soil present, the data will present an inverse soil response, and that's what you're seeing at the high frequencies, that divergence, the in phase trending upwards and the quadro trending downwards. This would not be detected using current EMI methods due to the frequency range. And then here I have data from a VS 1.6 anti-tank mine at 3-inch depth. The mine has a small amount of metal with a plastic shell and an air cavity on the inside. We would expect to see a metal and void classifications in the EMI response, and that is the case. There is a metal response, which is the broadband in-phase response seen at lower frequencies, less than 2 megahertz. And then again, due to the air cavity, we see a void response at higher frequencies, 2 megahertz and above. So HFEMI presents additional classification method, void and metal together, not available using current sensing methods. Here we have a VAL 69 anti-personnel mine at 1-inch depth. The landmine has a plastic body, but there is steel content inside that is accelerated upon triggering. This target should produce a metal response from the steel and a void due to the plastic shell and air cavity. And again, both the metal and void classifications are seen. The metal presents broadband in-phase signal, and the void presents as the in-phase and quadro divergence at higher frequencies. And this is a large metal response, so you actually see the void and the metal superimposed upon another, but it's just the data shows the classification and detection not capable with current EMI technologies. And here I have data from a carbon rod pressure plate at 2-inch depth. So we would expect to see a carbon rod response, which is a quadro peak around 1 megahertz, and that is highlighted in the plot at around 1 megahertz. and the wire begins responding around 2 megahertz. Even though the wire is metal, it's a small diameter, requiring high frequency or shorter wavelength to excite currents, generating the EMI responses above. The carbon rod and wire would not be easily detectable with current sensing technology due to their operation frequencies. And here I have results from a 28 gauge wire, 1 meter length at 2-inch depth. As expected, we see the wire respond at higher frequencies due to the shortened wavelength of the primary field, exciting wires on the current, and this results in higher frequency EMI responses detectable by our sensor, HF-EMI. This data would not be detectable with current sensing methods because it does not extend to these frequencies. To summarize what we've done, we've developed a handheld system. The system demonstrates the ability to detect and offers classification capabilities of IEDs, landmines. And then some of the components it can identify are carbon rods or carbon fibers, short wires, voids, small metal content. And the system uses an FPGA board for transmitter signal generation, analog to digital conversion of the receiver signal, and IQD modulation. And the system testing took place at Fort Apey Hill. And then we'd like to acknowledge and thank the Office of Naval Research for supporting our project. And that's where I'll conclude my presentation.
Wonderful. Thank you very much. We do have a couple questions, Randall, and we have some time. Thank you for being right on time. First question, what is the speed you have to swing the detector at to detect the PFM1?
So we collect data at about 3 hertz. You don't need to swing the detector at all. You can survey it similar to a like advanced EMI system.
Okay, great. And I had a question, maybe I missed it. Just how lightweight is lightweight?
6 pounds.
Okay. And can you go back to one of the charts? We had a question about what are on the axes there. If you have a second just to go into a little more detail. Yeah, like that slide there, for instance, on what we're looking at here.
Yeah, absolutely. Yeah, so so for in-phase and quadrature data, it's a unitless. It's we use a processing method of data minus ferrite over divided by ferrite minus background. So it's this complex subtraction and division. But it's unitless and it's normalized to our ferrite, which will provide like one broadband, like 1 across all frequencies, and then on the in-phase and 0 for quadrature. But so you have frequency for the domain and just unitless amplitude in the range. And then for the advanced classification, we have so time is on the domain, and for the range, it's current normalized volts, so more arbitrary, not ohms, but yeah, just current normalized EMI responses.
Okay, great. And we did have another question, but unfortunately we're out of time, so we'll have to circle back to that at the end so we can make some time for our next presenter. That is Motoyuki Sato from Tohoku University. And again, I'm showing just how uncultured I am. I apologize for any mistakes that I'm making in my pronunciation. His presentation is on dual sensors for humanitarian demining and its activities in Cambodia and Ukraine. He has been a professor at Tohoku University in Japan since 1997 and is the CEO of Alisys Company, where he works on ground penetrating radar, borehole radar, electromagnetic induction sensing. And we can hear you.
Thank you very much for introduction. I'm talking about the dual sensor. This is a content. Okay. is the content of my talk. I'll just briefly talk about our dual sensor, which we have developed. And the main technical topic of our sensor is the capability of the three-dimensional GPL imaging. And then we have tested more than 5 years in Cambodia, and quite recently we have started to use it in Ukraine. Okay, this is a demonstration of the operation of our system. Our system ARIS, which stands for Advanced Landmine Imaging System. So the sensor would be scanned manually by hand on the target, and then the data will be sent to the Android smartphone. And the signal will be processed and the image appears on the smartphone immediately after the data was acquired. It takes maybe 1 or 2 seconds. And then the right figures shows the two figures. The top figure is a metal detector and the bottom figure is a GPL. And now the GPL images moves because this is a three-dimensional configurated three-dimensional images, and now we are changing the depth, so the image also changes. These are basically horizontal slice of electromagnetic induction sensor, metal detector sensor, and the GPL. Our EMI sensor is a differential type. It has 2 receiver coils, so we have a positive and negative responses to the one metal object. Therefore, we can see now the red and blue color. And at the middle of the metal detector response, we can see the GPL response as a circle. So GPL image is represented from the electromagnetic wave reflection from plastic body of the anti-personnel landmine. So it is quite important to know the sensor position for these processing. So position information of the sensor is currently acquired by the accelerometer, and the three-dimensional position of the sensor is tracked while the EMI and the GPL data are acquired. And the GPL signal is processed by using sense aperture radar processing, or normally we say the migration, and then 3D image will be reconstructed. And then horizontal image of the target can be visualized, and we think it is a quite reliable information for the miners. Dual sensor is a quite common concept in humanitarian demining. It's a combination of the GPL plus EMI sensor. So this is a quite simple example. We have GPL image on the left figure and EMI sensor response on the right figure, and we have 2 targets. And the metal coin is a response to the right object, and the plastic mine is a left object. So in our concept in ARIS, at first we will use EMI sensor as a primary sensor to detect a metal object. In actual humanitarian demining operations, quite a lot of metal fragments is a serious problem because EMI sensor cannot discriminate actual mines from metal fragments. So EMI sensor detect both of them. But if you use a GPL, GPL can provide us as an image of the buried object. And small metal fragment does not show up on the GPL image, but the plastic anti-personnel mine, so the anti-tank mine, gives a clear image of the object shape. So then the miner can judge the object. So unique point of ARIS is the data acquisition is manually done, and it is not a straight scanning, but it is scanned as can be seen on these figures. So right figures shows one example of the trajectory that the sensor has moved. So typically, the deminer scans the sensor head in the area about 70 centimeter by 70 centimeter. And the left figure shows that the vertical section of the GPL image is plotted along the trajectory. So trajectory is folded many times, typically the 4 times folds, and then a vertical GPL profile is attached to that one. So in many cases in GPL, the scanning line is a straight, and the vertical GPL profile is also projected on a straight line. But the ARIS gathers a data set in a two-dimensional way, two-dimensional scanning. Therefore, the data structure is very different from the normal GPL data acquisition. So using these two-dimensional data acquisition, we can reconstruct the image in a three-dimensional way. So signal processing is migration. And then if you acquire the data around the target, the migration works. And if the data density is quite enough, the data quality can be also improved. So conceptually, we should scan the GPL antenna on the target. And as I said, typically 70 centimeter by 70 centimeter to have the enough size of the thin-scale aperture radar processing. If the data acquisition area is too small, we cannot have the very good data set. So the data acquisition and the position information acquisition is essential in our sensor. So GPL data is commonly used, displayed in the 3 manners. So A scan is a one-dimensional data set, and B scan is a vertical profile, and the C scan is a horizontal slice. So ARIS uses C scan, and we think it gives a very good information, rich information to the deminers. There are a few types of the dual sensor which is used for demining, but most of the dual sensor have the B scan display, not a C scan display. And from our experience, the B scan image is very difficult to understand because in real situations, the GPL is very sensitive to the homogeneity of the soil, and there are so much clutter included in the B scan. And the C scan gives a much better information. So this figure explains the situation. This C scan stacked on vertically, and this is a quasi three-dimensional representation of the GPL data. And the left figure shows the raw data, just plotted the data on the positions. And the right figure shows the images after sub-processing or the migration process data. We can very clearly see the target on the right figures, but in the left figure, it is very hard to understand the position of the target. Actually, this raw data is used to get this migrated image. So we have understood that the migration is not only image reconstruction, but it has an effect of the clutter rejection. So it is due to some kind of the spatial averaging of the data, which reduce small deflection from the small inhomogeneity. It is normally the clutter in a reconstructed image. So that's why our system can provide the horizontal image very clearly. So these are MATLAB codes that we analyze the data set. The data is acquired in the frequency domain from 600 megahertz up to 2.6 gigahertz and converted to the time domain and then processed for the migration. Okay, this operation of the ADIS in Cambodia at the last July 2022. And in Cambodia, it has been used for more than 5 years. Okay, these are data that we obtained from the Cambodian Mine Action Centers. From 2018, the two units of the ADIS was introduced in the Cambodian Mine Action Center. And from 2023, from last year, 14 units of the ADIS is operated by the Cambodian Mine Action Centers. And half year in 2023, ADIS detected 72 mines and 97 UXO. And it shows that the ADIS is working quite well in the Cambodia mine fields. And we have evaluated the operation of ADIS in several mine-affected countries. One of that is Bosnia and Herzegovina. We conducted a NATO Science for Peace and Security program last 3 years, and 4 units of the ADIS have used in Bosnia and Herzegovina. So this is one of the data sets that the Bosnian deminers has acquired. ADIS shows a very clear image, and he found anti-personnel landmine that is shown in these pictures. And from last year, we have started to work for Ukraine. So the Japanese government is supporting our sensor to be operated in Ukraine. And now 54 units of the ADIS was delivered to the Ukraine last year. Okay, this is a training of the ADIS operation in Ukraine. Okay, dual sensor is still a new technology in demining, and especially GPL performance is very somewhat very difficult to understand. That's why we continuously support the operation of the ADIS in Ukraine. We need a technical and scientific support that the GPL system can work correctly. So summarizing my talk, dual sensor with a 3D GPL imaging, ADIS was developed, and it has been deployed in mine-affected countries. The advantages of this sensor is there are several advantages that I have not mentioned in my presentation. Metal detector, EMI sensor response is also visualized in ADIS. So we found that in some cases, discrimination of the two closely located objects can be also achieved by using the EMI sensor response. And that kind of the condition can be quite often seen in Ukraine. So the landmine situation, the buried situation in Ukraine seems to be quite dense compared to the situation in, for example, in Cambodia. So such an closely located the object have to be separated in some cases. And then object can be visualized before excavation of the prodding. So it can improve the excavation safety. And if the object is not a mine, but just a metal fragment, we can skip it. So speed up the operation can be achieved. So far, ADIS has been deployed in the mine-affected countries in Cambodia, Bosnia-Herzegovina, and Colombia, Ukraine, and the Laos. It's Kratak bombers. And then, as I said, we are continuously technically supporting the operation of ADIS in these mine-affected countries. So thank you very much for your attention.
Thank you for the wonderful presentation. We had several questions. We'll see how many of them we can get to before we take our break here. The first question was, is it possible to mount this system on a UAV for tests in the Ukraine?
Yeah, we are considering about it. Yeah,
Okay.
in general in humanitarian demining, the mines are located maybe 5 centimeter or even 10 centimeter below the ground surface, because land mines are left on that position maybe more than 20 years. But in the situation in Ukraine is completely different. It is still the
Active war zone,
war
right?
situation, and the landmines will be laid on the ground surface or buried in very shallow conditions. So it will be possible that the GPL can detect even if it is mounted on a UAV. So, but from our experience, the GPL penetration will be drastically reduced if the antenna is raised maybe 5 centimeter above, no, not 5 centimeter, maybe 10 centimeter above the ground surface. So it is not easy, but if it the landmine is very close to the ground surface, it would be possible. So we are considering about it, but we still have not done it.
Okay, thanks. And another question, what is the central frequency for your GPR system?
Yeah, so this is a step frequency continuous wave system, and it operates from 600 megahertz up to 2.6 gigahertz.
Okay.
And it is a cavity back spiral antennas. So the operational frequency is really the wide frequency range. So we don't have the concept of the central frequency. It is a very widespread frequency range.
Okay. Follow-up question, for migration, do you use a constant velocity based on the type of soil, or do you fit the hyperbola?
Basically, we assume the constant velocity because antenna is supported maybe 3 centimeter to 5 centimeter above the ground surface. And based on our experience of the theoretical simulation, that the standoff distance from the ground surface to the antenna is almost negligible. So we use a constant velocity migration.
Okay, thanks. There were several more questions. We'll have to save those for a little later. They are in the Q&A, and we'll return to those. We have a short break now, and I need to ask Jasper or Lori, do we have a virtual demonstration? We do not. So we have a 20-minute break. Is that correct before we return?
That's correct. Mm-hmm.
Okay. So yeah, we have a break here, and then we'll come back and I'll hand things over to Jasper for the rest of our presentations.
I hope you had a good break. So we will begin the second half of our day after the wonderful first presentations. My name is Jasper Bauer. I'm the co-founder of the Demining Research Community, a nonprofit in humanitarian mine action, and the co-founder of SafePro AI, developing technology for landmine detection. So for the first half, or the second half of the day, we'll kick off with Davorin Ambrus from University of Zagreb. I had the pleasure of meeting Davorin in Geneva a few years ago, so it's very exciting to see where his research is taking him, and he'll be talking about the identification of buried landmines in mineralized soils. All right, Davorin, you can take it away.
Hey, thank you, Jasper, for the kind introduction. So I hope everyone can hear me. Okay, I will share my presentation. Okay, so thanks again for the introduction. So my name is Davorin Ambrus. I'm the lead researcher at the University of Zagreb Faculty of Electrical Engineering and Computing, and I'm really happy to be presenting here and given the opportunity to present our research. So just a brief overview of who we are. So we come from a small European country called Croatia, so the capital of Zagreb. We are part of the University of Zagreb, which is the largest university in Croatia. So our institution is called FAIR, the Faculty of Electrical Engineering and Computing, and we all form a rather small research group that is called Laboratory for Intelligent Sensor Systems. So we are not geophysicists, we are mostly electronic and electrical engineers specializing in EMI sensing technologies, and we do different research related to the application of EMI sensing to non-destructive testing, precision agriculture, and lately humanitarian demining. So how we ended up here? So our research journey started, let's say, 12 years ago. So back in 220, actually Croatia was still a heavily mine-affected country. So on the right-hand side, you can see the picture of Croatia, and the red dots actually represent the mine-affected areas still left from the war that we had during the 1990s. So there were about 700 square kilometers of mine-suspected area and more than 90,000 landmines buried in the ground. So at that time, our group actually was contacted by the Croatian Mine Action Center to see if we can do some collaboration and help with our expertise in EMI sensing. And so we actually start discovering this whole new world of humanitarian mine action. We got new kick-off grant from the Sir Bobby Charlton Foundation, and things kept rolling. So when you look, 12 years later, here we are. What's changed? So Croatia is still not exactly mine-free. So I mean, the situation is much better now, but we still have around 90 square kilometers of mine-suspected areas with almost 10,000 buried landmines. Many lessons have been learned during that time, both from our point of view as researchers, as well as in the mining community. But what is, from our perspective, still striking to see is that the state of detection technology has really not changed that much from that times, in the sense that we see that many research efforts have been put in the past decades, trying to develop different technologies to help with the mining, especially in the humanitarian sector. But there has been very low takeoff of the new technologies, and pretty much the only devices that the miners are using nowadays are the handheld metal detectors, and to lesser degree GPRs and dual sensors we've seen in the presentation before. Why metal detectors? I suppose you probably all know what kind of devices are those. I will just briefly go through some main features. So these are the EMI devices that can operate both in frequency domain or time domain. So their biggest benefits are that they have excellent sensitivity, so they can detect even the tiniest amount of metal in any type of hazardous device, so plastic landmines, stuff like that. So this translates to very high probability detection. They're robust, they're high speed, and they're rather cheap. So this is their main benefits for use in humanitarian demining. Of course, their biggest drawback is that they are non-discriminate. They really cannot differentiate between metal part of a landmine or some harmless piece of clutter. And this actually translates into extreme false alarm rates, which can go from, let's say, 100 to 1,000 false alarms per one hazardous object. So this work in humanitarian mining is well regulated by international mine action standards. The procedures are quite different than those usually used in UXO, let's say deep search UXO service. So the mining work is usually done in lanes. These are actually these are lanes typically that have typical width of 1 meter, and the miner is usually doing a zigzag sweep of the metal detector, and then they slowly progress into the mine suspected area. So the procedures declare that every alarm that the miner encounters needs to be checked. It has to be checked with a prodder, and every suspicious object needs to be excavated. So then, I mean, taking into account these huge false alarm rates, you can imagine the frustration of the miner when he needs to dig for like 1,000 times before he actually excavates an actual landmine. So this is a really tedious work, and it often results in loss of concentration of the miner, and loss of concentration usually fortunately lead to accidents. So if that's not enough, there's also the soil problem. So as we may know, there are many soils around the world, especially those with high content of iron, which cause quite problems for metal detectors. In Croatia, we have the soils, we have those karst terrains close to the Adriatic coast, which can be easily recognized by the red color of the soil. There are also many soils throughout the world in tropical areas, volcanic soils that cause similar problems. So this is a well-known problem for metal detector, and usually all the detectors used in humanitarian demining must have some kind of soil compensation to be actually useful. Although this helps a lot in the mining work, there are also important limitations. Most of the methods used in such devices are proprietary, so you cannot really know how the actual compensation works. They are oriented strictly towards metal detection, so the methods usually enable to get rid of the soil signal, but it actually heavily distorts the characteristic response of an object, or it can actually kill all of its information content. So practically, this is not useful for anything besides basic metal detection. In practice, they also reduce sensitivity, which can be dangerous because you can miss some of the mines buried in such soils. And there are also practical issues with liftoff because some of the methods require that the constant liftoff during the operation of a detector, which is practically impossible to obtain. So now we come up with our research challenge. So taking into account that there has been such a low takeoff of new technologies, so we came up with an idea to use an existing piece of equipment like a handheld metal detector and try to do some upgrade of this technology by adding some new features both in terms of hardware and software, so that this kind of device is turned not to a metal detector but actually to a landmine identification tool. And we would also like it to test it and to be able to work in realistic conditions, which includes also mineralized soils. So there are many challenges with this approach. First of all, when you look at the picture of a metal detector, you immediately notice that the geometry of typical metal detector is quite different to the geometries of EMI sensors that are used, for example, in UXO search. So unlike those detectors that can be used for advanced geophysical classification that feature multiple transmission receiver coils, we are stuck with a single transmitter and receiver. In case of pulse induction metal detector, you typically will have only one coil, which is used both as a transmitter and as a receiver. So you have to cope with that because as a result, you get much lower spatial diversity of EMI data. The other important thing is that when you look at the object to clutter size ratio, the things are getting much more different because in realistic demining operations, metallic clutter can be on the same order of size as the metallic parts of landmines, which is also very difficult to handle. And of course, when you look at the total responsible metal detector, the physics behind it, then you can easily see that there's a very complex interplay going on between different parameters such as object location, electromagnetic properties of the object. So it's conductivity and permeability, its geometric attributes, sensor geometry, the way you interrogate the sensor, and of course the soil. So the bottom line, what do we need? So if we want to use such a detector for those purposes, we need some kind of a scanning type positioning assisted EMI system. So we want the detector to be able to sweep over our target to get a position of that detector and to be able to, let's say, illuminate the buried object from all possible sizes and get out the most quality data that we can. And of course, we need efficient data inversion methods to decouple the object's intrinsic and extrinsic properties, so then we can use those intrinsic properties, the signatures of an object, for, let's say, object identification. So this is our proposal, our solution to this problem. So this is our demo system that we designed. It actually consists of a commercial pulse induction metal detector. This is a Valon VMF4 type. This is actually the latest generation metal detector. It's used in the humanitarian demining. It's quite popular in demining operations. We had a collaboration with the German company Valon, the producer of the detector. So we got access to the raw data of this detector. So we're only using raw signals that come out of the search head. And in addition to this detector, we also designed electromagnetic search head tracking system. So this is the wood thing on the ground here, which actually enables us to track the position and orientation of the search head in real time. And of course, the software, which handles all the pre-processing of signals, detector tracker synchronization, and data inversion and object classification. I'll just briefly describe this crucial piece of hardware that we developed. This is a search head tracker. So it's electromagnetic based. So this is a first generation of this tracker that we devised. It's basically a wooden stick, and inside the stick there are two triaxial magnetometers, which actually capture the magnetic field coming from the search head. And based on that measurements and knowing the known distribution of the magnetic field between the transmitter and the sensors inside the stick, we can then estimate the relative position and orientation of the search head relative to the stick. And this works quite nicely. It works in real time. It has like 2 to 3 millimeters accuracy in position and sub-degree accuracy in orientation, and it can provide us with the 5 degrees of freedom position and orientation of the search head, so we can measure the X, Y, Z position, the pitch and roll angles, and we cannot measure the third one, so the yaw, because of the symmetry, the circular symmetry of the coil itself. So we validated this stick in laboratory and both in the field, and now we have also developed the second generation of the stick, which so we have moved away from this ugly wooden thing into this more cool plastic thing you can see here. This is still we are still testing it, so this is pretty much has the same functionality, but the whole electronics is embedded into this stick. So the idea is to use this tracker. You just put it on the ground, turn on the detector, and you get data from the tracker and the metal detector, which can be streamed wirelessly over Bluetooth or Wi-Fi to the PC, and then you do all the inversion and classification on a PC. So if you're interested more in more technical details of this tracker, you can check our publication here. Okay, so the approach to the whole landmine identification can be seen in this block diagram. So the idea is we use the EMI data coming from metal detector and the positional data coming from the EM tracker system. We synchronize those data, and then the signal processing is actually handled in 2 steps. So the first step is physics-based. So we use dipole models and for the targets, and also some kind of dipole-based models to model the soil, to invert for the object location, to do the signature extraction and soil compensation. And once we have those signatures extracted, so those signatures are actually target polarizabilities, which we then feed to our machine learning algorithms to classify whether it is a landmine or something else. So the whole procedure looks like this. So you have a tracking stick on the ground, you have a sweeping metal detector doing some kind of zigzag trajectory, you acquire data, and then you do the processing on a PC. So of course, once we devised the system, we first tested it in the lab. So we did quite a lot of experiments in our laboratory. We used different metallic objects. So we placed the objects under the objects under the platform, which is kind of an improvised platform, which is just put in the air so that we avoid some excess metal content of in the floor and in the surrounding laboratory. So we had a couple of interesting objects. So these first two are actually some parts of surrogate anti-personnel landmines. This is a PMA2. I will mention that landmine later on with very low metallic contents. This is just a small aluminum cylinder. So we got PMA1. This is a bit somewhat larger aluminum cylinder, and with some other objects which actually represent, let's say, clutter objects. And you can see here some of the examples of the extractive signatures. So again, when I talk about extractive signatures, this is time domain signal. So this is actually polarizabilities. So the magnetic polarizability tensor eigenvalues in time domain of each object. So this is this is the anti-personnel landmine surrogate. You see it here, the metal part, and the extracted signature actually corresponds to a non-magnetic cylinder, and the system was able to very clearly distinguish that as a signature from a non-magnetic cylinder. This is a question. This is an example of a beer cap. So again, the signature is quite unique, characteristic, and again the system was able to recognize that it is a steel bottle cap, and we were also able to estimate the position and depth of the objects correctly. Okay, so we also did some classification work using those signals acquired in laboratory. We got a perfect score, but okay, so life is good, and we were happy, but we know that it's just the first step, and that these measurements in the lab are not really the representatives of an actual environment. So we went to the field. So for that purpose, we used the test site Jazbina. This is some kind of an improvised test site on the outskirts of Zagreb. It's actually just a piece of land which is owned by the Faculty of Agriculture. And then we arranged two, let's say, measurement, I would say, how do we call it, measurement holes. One of those was filled with local soil, which is slightly mineralized, and the other one was filled with red soil, which we arranged to be to get the red soil from the Istria County in Croatia. And actually, we used a bit more different metallic objects, buried it in both of these pits. And we buried the objects at different depths, from 3 centimeters to 15 centimeters, using different orientations and in two types of soils. So we were interested. Our most interesting part was, okay, so what's the worst case scenario? So we would like to see if we can do the worst case scenario because if we are able to do that, then we are probably on the right track. So our worst case scenario is, again, this PMA2 landmine. This is actually a landmine that is quite often found in Croatia and Bosnia and the whole Balkans. So it's a former Yugoslav anti-personnel mine. So it has a full plastic body, and the only metal part is this small metal aluminum fuse right here. So if we are able to not just detect but actually identify this small metal piece in red soil, then I guess we will be happy.
Devrin, you got 1 minute left for.
Okay, thank you.
For time.
Okay, so these are the results. So you can see the responsible metal detector, which is quite heavily influenced by the soil, but actually our system was able to separate those two things, the soil signal and the object signal, and the classification was actually correct. So we were able to identify the object as a non-magnetic cylinder up to some 7 centimeters, depth of some 7 centimeters. We also did some classification. So in red soil, our classification score was quite good, so about 97.6%. So the only misclassifications were related to those two landmines, PMA1, PMA2. If you remember, those are two aluminum cylinders, so quite similar objects, which is really not that surprising. And we got slightly better results in slightly mineralized soils, which is kind of expected. So our ongoing research is related to the deep learning algorithms for object classification. So we're working on improving our algorithms for signature extraction, localization, soil compensation, and also trying to maybe use some simulations to train our object classification algorithms. So here are some recent research results that you can check out if you're interested. And to conclude, So we have developed a demo system which is able to reliably extract orientation-independent signatures of buried objects. This can work in mineralized soils, so we're able to provide very effective soil compensation without significantly distorting those object responses, and we can do some object identification. Those realistic conditions. We are now continuing to improve the system, and of course, we're looking for new demonstration and collaboration opportunities. So thank you very much, and I'm ready for questions that you may have.
Thank you. We'll take questions at the end of the session. That was an excellent talk, and I'm sure there's going to be a lot of really interesting questions. So our next talk is Sophia Bragdon from USACE, a lot of acronyms, ERDC, CRREL, CREEL. Okay, Sophia, you can take it away.
So yeah, I am with the U.S. Army Engineer Research and Development Center, which is under the Army Corps of Engineers. And so I'll be talking about some work that we are doing at CREL with my program manager, Jay Clausen, on IED and mine detection for warfighter support and ways we think this might be applicable to the demining community. So, as all of you are pretty familiar, it's near the end of day 2 of this conference, and there's a lot of different approaches to humanitarian demining. A lot of them are ground-based type systems, and there's inherent danger in doing ground-based systems. You're close to the explosive hazards, and that is a threat to the operators of the sensors and also the people addressing the explosive threats for mitigation and remediation. So going on, as again has been talked about recently, there's some common approaches. Like there's some talks about the metal mapper, which is a ground-based system to find buried objects underneath the ground, and some other various sources that require a person on the ground for the most part. They could be airborne, but a lot of what is being done is on the ground surface. And like I said, that's inherently, dangerous and also not as applicable in the military warfighter support setting. And so I'll go into a little bit about what we're doing and how it's related to this humanitarian demining problem. So we're doing work under a counter IED program for the Army. And the goal here is to do standoff detection of surface and buried targets, which might be landmines or IEDs or other explosive hazards. And the platforms are likely going to be Group 1 UASs outfitted with a various suite of sensors such as maybe radar, EO, IR, in the long wave, mid wave, looking at polarized hyperspectral. So there's this whole suite of sensors that may be put onto these Group 1 UAS that will have data processing on the edge to give real-time notification of potential targets, both, like I said, surface and buried. And in the warfighter support setting, we have a big interest in speed, and also in being kind of stealthy in your detection. So walking around on the ground with a ground-based system is not going to be as applicable in this warfighter support setting. So that's why we're focus on that standoff detection. But we also believe that standoff detection is going to be useful in this humanitarian demining arena. And the big difference is how much time you have to actually go and find the landmines or buried mines. And we foresee in the humanitarian demining arena, we could use our approaches, but use time as another factor that we can leverage and maybe take multiple looks at different times a day or under different conditions because we know our sensors are affected by environmental operating conditions. And so our focus here is I'll be talking about using long wave infrared imaging. And so we're in the thermal band. So we're focused on finding a thermal signature on the ground surface induced by the presence of some buried thing under the ground or a surface target. And we have found that the terrain and environmental conditions hamper the performance of aided target recognition systems, or AITDRs. And so there's inconsistent and unacceptable probabilities of detection and false alarm rates for especially subsurface targets using thermal imaging. And same issue would be applicable to remnants of war cleanup with using long wave IR. And a big challenge here that we're facing is that the thermal images have very low signal to noise ratios when we're trying to find the buried objects. And so you can see some very small example images. We'll go into some more data later of there's a lot of thermal clutter induced from the background, and how do we increase that signal noise or mitigate the issue that there's all this thermal background noise so that we can actually pull out the targets of interest from these noisy thermal scenes. And we have this whole pipeline that we've been working on at CREL where we've been collecting a lot of data. We are developing a two-step AITDR, which I'll talk about in more detail later, and bringing in those environmental information to better detect and classify our explosive hazard threats within these thermal image scenes. And so let's get into an example here where here's an example of some data we collected in Panama in a jungle environment, just to give you an idea of the kind of challenge that we're facing with using long wave IR. The dashed boxes on that image are buried mines, and the solid boxes are surface mines. And then we have a various looks at signal to noise ratios for the buried targets here. And it's not great. We're on the order of 1, so the signal of the target is about the same order as the noise for the buried objects in this scene. And so it's a really challenging detection and classification problem when we're dealing with this much noise. And you're also seeing a time series of some of the environmental conditions that are impacting the visibility. And one that is really important is soil moisture. And when that increases, we have less visibility. And we were in the jungle during the rainy season, so it was a very challenging environment. So this is just one example of the type of data we're working with. And so how are we addressing this? And first step is we need to figure out which of these environmental factors are actually impacting the visibility of buried objects within the thermal imaging. And we could go directly from the environmental data to the thermal image and study that relationship. It is possible, but it requires a lot of computing power and it is just computationally difficult. But we could instead introduce these object variables, which are basically representing the visibility of our buried objects within the thermal image. And then we can get a nonlinear relationship that we can model between the environmental data and those object variables. It's going to help us understand when we can see the objects, when we cannot, and when is the background noise going to be really prohibitive. And here's an example of our test bed that we have at CREL in Hanover, New Hampshire, where we collect a lot of the data where we've done development of our algorithm with. So for those object variables, we are using just some basic statistical representations where we're using first order statistics and we're calling these contrast metrics. The first two are related to Michelson contrast, which is commonly used in like computer vision applications to amplify contrast in the image. You can use it as like a mask on your image. Here we're just saying, all right, we know where our buried objects are, so we can actually compute the contrast metric with some local background for our images. And here's an example where there's 4 buried things in this image. The shallow ones are buried at 5 centimeters below ground surface, and there's deep ones in the top corners that are buried at 15 centimeters below ground surface. And then in the table here, we have highlighted for these shallow objects, we can see that when we're seeing the objects, the order of magnitude of the contrast metrics for the visible objects is, greater than when we're not visible. So that's just kind of a sanity check. Is it reasonable to be using these contrast metrics? And it does make sense in our application to look at contrast metrics as a proxy for target visibility. So then we take those contrast metrics and various groups of them for the target classes, and we project them onto the principal component using principal component analysis. So then we have just one metric to work with versus a collection. And this plot we have here is showing the distribution of this contrast metric measurement, where we computed the metric in the location of the shallow plastic object before we actually buried anything, and then after, and we see a shift in the distribution. So there is something being captured by this contrast metric that we're using to measure visibility. So then next, we are mapping the environmental data to the contrast metrics, and we're using a machine learning regression model to learn this nonlinear relationship. So we're taking an input of the environmental variables, and we want to predict the contrast metric. And we're doing this using a neural network called TabNet, which uses attention transformers rather than a kind of a classical feed-forward neural network to learn this regressional relationship. And what's beneficial about this algorithm is with those attention transformers, there's a built-in feature importance measure. And so we can figure out, as the model is learning these relationship, which environmental factors are most impacting the correct prediction of the contrast metric, whether it's visible or not visible. So it's capturing all of those relationships. And in after training that model, here's an example on our New Hampshire data set that we can identify the most important environmental variables. So it's incoming solar radiation, relative humidity, soil water content, and the average air temperature. We do that for the different target classes that we have, different groups, whether it's plastic or metal, and we get a collection of 5 environmental variables that are most impactful on the target visibility within long-wave IR. And we're going to use that to better classify our detections that we get in our ATR that I will be talking about next. So Corel has developed a 2-step environmentally informed ATR, or AITDR, and where ATR is automatic target recognition. And so basically, if you're not familiar, a 2-step ATR has a detection step, and then it has a classification step that then ultimately tells you what you have. And in our approach, we're using our detection step as a computer vision approach, where we are not using machine learning, and we are leveraging image processing and some traditional computer vision approaches to produce our detections in a reliable way. And then we get a collection of ROI nominations or regions of interest that may or may not contain something. And there are a lot of false alarms. And we do that to reduce the false negative rate, because we can handle the false alarms in the classification step. And we're bringing that environmental information we just looked at previously from that regression relationship into this classification to better feature out or filter out our false alarms And we're doing this using a feature level fusion between the thermal images and the environmental information. So quickly, the computer vision process here, the goal here is to enhance the signal to noise ratio by improving the contrast or increasing the contrast in the image and preserving edge structure and amplifying edge structure. So our first step is we're applying anisotropic diffusion to our raw thermal image after it has been normalized to smooth the image. Then we apply the shearlet transform, which is a methodology to filter out high frequency noise. It's similar to a wavelet transform, but it's anisotropic. And then we apply what's called the Sobel operator, which is essentially computing the discrete gradient at each pixel in the image. And then we create an edge image by looking at the magnitude of the gradient. And so that's going to amplify the edge structure where we have a sharp change in our gradient. And we do some thresholding there. Then we're combining our nice filtered image with our edge image. And then we are doing edge detection on that fused image to produce our ROI nominations that may or may not contain a target. And so we have found that the way we normalize the data is really important in amplifying the contrast. So that's what's here. I'm going to go a little quicker for the sake of time. Then we take those ROI nominations and we have to classify them. And so what we do here is in that classification block, we're using this architecture where we take ROI chips from the long wave image that were detected using the computer vision algorithm. We're putting them into a ResNet classifier, but it's modified. We've lopped off the last few layers. So we're using ResNet as a feature extractor rather than a classifier. Then we're taking those 5 important environmental variables we identified in the regression problem into a fully connected feed-forward neural network, which is again being a feature extractor. We are then concatenating, and that is our feature level fusion. And then we go into some classification layers to ultimately filter out the false alarms from the true detections. And some results, we tested on data collected at CREL and also in Yuma, Arizona at the YPP Proving Grounds. And when on the data sets that we've analyzed, our environmental two-step ATR is outperforming other methodologies from the literature, such as Deep Target, which is a two-step ATR for thermal images, and faster RCNN, which is a one-step object detection algorithm. And we also compared with some ablation analysis. Well, what if we only use the ROIs and use our same architecture, but we just took off the environmental part? Well, we're not doing as good as we did when we include that environmental information. So we can leverage our environmental knowledge to better filter out false alarms, and we can apply this to different environments, not just where we have trained on our CREL New Hampshire data set. It was generalizable to Arizona, which was really great.
And Sophia, we are short on time, but the good news is we don't have a lot of questions yet.
Okay, I am almost done. And so something that we have is a big data set. And so if you're interested in long wave IR data containing buried objects, please consider reaching out. And just so some conclusions. So the Army setting and the warfighter support needs the standoff detection using passive sensors. You can cover large distances quickly, and you can also couple the long wave IR sensing with other modalities for finer grain identification. And so in the humanitarian mine application, you can narrow down to say, hey, this area has a lot of different targets. Maybe you should spend your time looking at targets there. And when we're bringing the environmental information into our algorithm and classification process, we greatly improve the accuracy. And I'll end with questions and our contact information if you have further inquiries. Thank you.
Excellent. That was super interesting. My background's in computer vision, so I really appreciated that talk. I have a lot of questions for you, but in the sake of time, we'll move on to our final talk of the day with Craig Locke from Tetra Tech, and he will be presenting on the operational optimization of 3D modeling. And this is a project also that was presented at in Geneva. So Craig, you can take this one away. Thank you.
Okay, so as introduced, I'm Craig Locke, and I'll talk you through operational optimization through 3D modeling in Old Mosul, Iraq. Erin Atkinson was due to be presenting, and she sends her apologies, but she's had to go and present in Geneva this week. Now, the problem we face in Iraq, dense urban clearance. The DMA issued us the task of clearing Old Mosul. It's a part of the city that's as culturally significant as it is battle damaged. It was the last stronghold of ISIS in Iraq, and during liberation, the city suffered from an incredible amount of battle damage that we have been tasked with making safe. Now, the image on the left is Old Mosul as it stood in 2016/2017, overlaid with the polygon issued by the Iraqi Directorate of Mine Action. It sits at approximately 281,000 square meters. The image on the right, however, is our first flight. As you can see, many of the colors that were previously present, many of the buildings that were previously present have been destroyed, reduced to rubble. And the buildings that are still standing are battle damaged. The sheer scale of the damage alone is what led to us requiring an alternative approach to planning operations. A 2D desktop study works when your site's 2D. A CONUS range clearance, for example, is bread and butter, whereas this is a beef Wellington. Now, it's a problem of scale. How do you eat an elephant? The issued 281,000 square meter polygon doesn't take into account the 3D nature of the site. The truth of the matter is we are 49% complete of the polygon, but it's comprised of 3D multi-story buildings and over 3 stories deep of rubble, which is littered with explosive contamination. It's taken us 2 years to get this far, and from that 281,000 square meter polygon, we've cleared over 545,000 square meters. Now, the searcher you can see on your screen has to go through all of this rubble by hand. There's 281,000 squares become 545,000 squares when he's got to repeat the process over and over again just to find a safe hard surface. He goes through each piece of rubble by hand, as there's suicide belts, improvised grenades, conventional munitions buried throughout. On top of that, we've processed 596,000 cubic meters of rubble. The depth of the excavator is the level we're having to go down to find safe land. We estimate that there's over double this to go in both square meters and cubic meters. Now, to achieve our task, we need to manage our resource allocation, including our mechanical assets and our equipment, our demining teams and the deminers, and the organizational staff on top of that, our operations managers and our technical field managers. We've got to do this to a fixed schedule and budget and manage the expectations of both our donor nations and the Iraqi Directorate of Mine Action. How do we do it? Our solution has been to drop back, well, to push forward even, onto drones, photogrammetry and 3D modeling. We used a fleet of Autel Evo 2s off the shelf with an 8K sensor. And we trained our local national operators to plan and fly the missions. Both our interpreters and team leaders are now proficient in conducting their own missions. They're not only using the UAVs to build 3D models and to facilitate new imagery of new sites for going to clear, but to access areas that can't be accessed either on foot or are too dangerous to access as the buildings falling down, etc., etc. Now, in total, it took our guys over 20 hours of flight time just to produce the model that I'm about to show you. They captured 8,600 images, and it was over 100 hours of processing time for both the refinement of the captured data and the processing in Pix4D Matic. The model was flown in October 2023, and we're currently in the process of reflying the whole site and picking up any areas that have had significant change since our first flight and clearance began. Now, building the model and processing the data. After the initial cleanup and removing images that weren't viable manually, the data was processed in Pix4D. The blue and green dots on your screen are the captured images, a lot of them. The vertical images were captured at 80 meters and the oblique images were captured at 40. Each of the points making up the image now are tide points, making up the dense point clouds that the software is flying over now. The software detects the overlap and similarities between multiple shots and drops a tide point, which is used to build the dense point cloud and render the model. The tide points are then supplemented with manual control points, spatially known locations that we can identify, and it increases the output's accuracy. Every day when our team leaders go out, they conduct a GPS check, and we can use those GPS checks to further refine the model. It's a lot of raw data to process, so we run it locally in a rack to avoid any connectivity problems. Now, this is the output model, and what it allows is data-driven decision making. It allows us to visualize remotely the site from top to bottom, 2D and 3D. It allows our operations managers to conduct strategic planning, so they can conduct phased clearance, they can locate access points, staging areas, and resource optimization. Explosive hazards can be identified from the model and from the imagery, and any buildings that are liable to be a threat that we can't access due to their structural integrity. Now, as we're panning around now, we're passing many sites that we've now cleared that will be updated within the next week or so. This is St. Joseph's Church. It's currently being rehabilitated by the United Nations. A lot of destroyed houses. You can see the problem we face with the sheer scale of destruction. Al-Matfi Mosque, one of the oldest in the region, and I'll touch back on that later. And all along the shoreline, that's rubble that was pushed by both the Iraqi army and previous clearance organizations who bulldozed a large portion of the city. Now we're going in with a more methodological approach to try and render the place safe without pushing it into the river. Now, this is one of our local national GIS analysts in country, showing how they process the data and how they action it. They conduct requests for both the technical field managers, our expat staff, and the local national staff. Now, luckily, they captured one of the front-end loaders while it was on site. It allowed them to measure the width of the roof, the width of the vehicle, and then they can take those measurements and process them further. So they can pan around, find alleyways, points of access, points of egress that wouldn't be easily measurable from the office. The operations manager is sitting at his desk. He's not going to know this from the top. He's going to try and push a front-end loader into a fixed area and only be told of the problems when the front-end loader arrives and he gets a phone call. Now, the FEL can make it up that alleyway, but it's not going to make it down that one. On top of this, going back to the scale of rubble, this was previously a house. There's still a stairway in the middle there, but it's multiple tons, and the costs way up. So when we're processing this rubble, there's a large volume there. The volume is calculated here by our guy as it's chewing away. There's 343 cubic meters approximately of rubble, which allows us to facilitate the pre-booking of trucks and vehicles to remove that rubble once it's cleared. It'll get pushed out by the front-end loader and then manually searched again. The same guy you saw fingertip searching through those heaps of rubble will again conduct battle area clearance and manual clearance if a threat's identified through that rubble before it's loaded up into a truck, processed and sent away to be deposited. Now, some of the outcomes and benefits. It allowed us to conduct a structured plan. We'd initially built a plan on the 2D 281,000 square meters alone, which didn't take into account the scale of work that was required. It's allowed us to effectively use our limited resources with input from multiple parties, both in and out of country. The model's hosted online now and can be shared as a full package. It's a few gigabytes, but it's feasible. It allowed for us to have other operating units and other staff consult where they wouldn't be able to make it into country. They wouldn't be able to provide assistance on the ground. Now, based on our refined estimate from the 3D model, we estimate that there's approximately 1 million square meters of 2D clearance required due to the depth of rubble on the riverbanks and over 1.3 million cubic meters of rubble for clearance and removal remaining. We've been able to optimize our clearance, our resource allocation and pre-planning has led to us having an approximate 25% reduction in clearance time. We've managed to model and plan clearance for over 500 structures, or at least the foundations of structures within our polygon. We've rendered safe over 38,000 explosive hazards that we found in the rubble. That includes 632 IEDs, over 1,000 IED components, main charges, initiators, detonators, and nearly 38,000 items of UXO. We're including suicide belts, improvised grenades, victim-operated IEDs, some of which have been identified from the imagery alone, and some of which we've been able to find in the model. Now, using the model and being able to identify properties and houses that have been either reoccupied whilst we're conducting clearance or have been reoccupied post-clearance has allowed us to provide bespoke outreach. We've estimated that there's been 50 houses either rebuilt post-clearance or people have moved back into mid-clearance, where we've been able to send explosive ordnance risk education teams to brief the beneficiaries and to brief the local officials who are conducting either remediation, rebuild, or trying to rehome displaced persons. Now, there's a side benefit to the model. The image shown there is an ancient bathhouse. It was blown up by ISIS prior to the city being retaken. The models allowed us to capture in time these historic sites, both before they've been renovated and during renovation. Now we're currently flying again, so there's going to be an update to the mosques and the buildings we've captured. So this is Al Masri Mosque. It was built in 638 AD. Prior to renovation. Now, the model's aided with both the justification for the site to be refurbished and has allowed for it to be visualized worldwide by interested parties. It's facilitated with the regional councils to seek funding from the wider government. It's allowed us to justify clearance. I finished a little short on time there, but that's I'm English and I talk too fast. Thank you for listening to my draw, and I'm open to questions either here or you're welcome to get in touch via email.
Yeah, thank you, Craig. We have some time. You left time for some questions. So any ones from the audience on this talk? If not, I have a question. In terms of explosive ordnance risk education, how do you disseminate, it's, a lot of gigabytes, these 3D models, how do you distill this information into things to educate the general population?
The last video I showed you, this one is a GIF. So we've pushed out GIFs of various sites to the risk education teams, and they push them on via WhatsApp to either local groups or to local people of influence, so local mayors, etc. They then push them out to their guys and disseminate them from there. We also push it out. The imagery is processed and pushed out via posters and leaflets. We stick up around the sites. So we push out as much as we can.
It's really an incredible scope. How much longer do you think it'll take to continue on this project?
We've probably got another 2 years. So we've cleared the access and egress so far. Again, in the background of that image, you can see those heaps of rubble. Underneath those heaps of rubble, there's houses. Every house had a basement. So you think you've cleared the surface, then you find an access point. You find a stairwell that goes down and opens up into a multi-story basement. And the basements were used for both storage of personnel and weapons. So there's still bodies down there. There's IEDs, conventional munitions. Not very nice stuff.
Well, are there any booby traps in a lot of these places? I know in Ukraine, where I've been working, a lot of the munitions and sites, trench lines are full of booby traps. Is that a concern?
Yeah, some of the IEDs are still live, so the power sources are still viable. And you'll enter a basement, there could be a crush switch at the door. We've had an ammunition vest, an ammunition rig hung up on a wall, but it was on a tension release cord. So if somebody had picked that up, it would have triggered a shaped charge behind the wall. It's pretty intense.
Well, thank you for that work and the presentation. So now for the rest of the talk or the rest of the conference, we have about an hour for questions from the crowd, and I see there's a large backlog of questions from the beginning part of the day, so maybe we'll slowly go through those and continue everyone in the crowd to put questions in the chat and we'll address them. Also, for presenters, feel free to respond to questions in the chat as well if you feel that you didn't have time to answer it properly. Harry, do you want to ask the questions from the beginning part of the day that we did not get around to from the first presentations?
Yeah, absolutely. That sounds great. I guess let me start by confirming I see John Jackson still on here. Great. I know we had some questions for you that we didn't have time to get to. I actually had one about hardware versus software for single pass or dynamic AGC. Is it a function of hardware or software? I guess there's some instruments that were being used for Q. So the instruments that were being used for Q that are now being used for one pass, did the hardware have to change in order to accommodate that?
That's a more complicated question than I think you might even be intending. So there's two answers to that. So there's the physics-based instrumentation software answer to that, which is you can do it. A lot of these instruments collect the same data, maybe at different data densities, maybe slight modifications between the two, but you can do it from a physics perspective. The second way of answering this, though, let's backtrack and remember the reason all this came about in terms of DAGCAP and some of our base of operations and quality control is to reassure the stakeholders and the regulators. And they want to know, after years and decades of us training them, we have to detect every piece of metal and then remove that metal from the ground in order to say we've cleaned up a site. They want to know, why are we leaving metal in the ground and what do we know about that? So they put a lot of emphasis on the validation of the equipment and software. So we do want to take it through the process of saying, yes, we've demonstrated this hardware and this software can classify, can do one pass.
Okay.
I hope that answers your question.
Yeah, thank you. We had another question about the applicability to marine systems, which I think maybe I know the answer, but I'll let you answer, John. Is there an AGC marine counterpart available?
Short answer, yes. One of my slides, I didn't mention it, but did have a picture of a marine system. The Ultratem has one that's operated overseas, including Europe. Again, the issue for us is, has it been validated? So right now, CERTA BSTSP, which is sort of the research arm of DoD, they are focusing on transitioning underwater technologies from the research side to the production side. And I know there's a lot of already commercially available stuff, but that's how we're viewing it, is the transition from research to production as we speak. So that's a very hot topic. How are we validating these instruments in the underwater arena? And unfortunately, I don't have an answer for you at this stage, but we do have sites where it's being used already. So we need an answer quickly.
And sort of a follow-up to that, how do we as an industry think we could learn from accreditation within the US and apply it to Europe and across multiple countries without a single organization to run it? Or do you feel that single organization is a requirement?
Yeah, good question. I'll take a rain check and say I want to think about the complete answer behind that for a little bit, but my gut reaction is I don't think a single organization is really required. We operate fairly well with multiple organizations as long as two things happen. One, communication between the organizations, and two, some sort of consistency between the two. So I think if those two things are met, we can continue the way we're doing. And there, as cliche as it is, each site, each country, each dynamic is different. And so making sure that your accreditation program or your quality program addresses what your needs are, I believe in that. So I think separate ones are fine.
Last question for you, John. Is the cost analysis in your presentation of current?
Jeff busted me. I saw that question come in. So it depends on how you define current. I'd say it's about 3 years old, which is a unique time frame to pull that from our perspective. So that was peak getting large contracts out, and by large I mean 1,000 acres. Here's what we need done on 1,000 acres. So we got a lot of one pass proposals at that stage. And I think there was probably a competitive nature in terms of certain companies wanted to get their foot in the door first to advertise they were capable of doing this. So we might have gotten a better deal on some of those projects when you compare the dynamic process. But that's actually why I had the footnote on the cost reimbursable and that, or cost plus fixed fee, in that I think that's a more honest answer in terms of how much would we have paid for labor and materials had we dug everything versus doing one pass. So I do think it's time to reassess that, but we didn't have the projects for me to perform that exercise again, but I think I will. If I were to give this in a year, I think I'd have updated numbers.
All right, we'll look for that next presentation. Moving on to Stephen and Craig, we had some questions for you about your presentation. One question I had was, would we see value to having 3 size bins rather than just 2, or is that site dependent?
Yeah, I think it is site dependent. For the site we were working on, we had that challenging geology, which can make the size estimates less accurate. The fortunate thing there is that those size estimates, when they're inaccurate, we're usually we're erring on the large size, so we have more conservative evacuation distances that are necessary. So on a site where we didn't have those challenges, yeah, I could definitely see multiple size bins being more advantageous. For this one, I think keeping it simple was the best choice.
Sure. And I guess Matt Barner had a related question. With regards to your size bins, was the large basically your maximum separation distance in your ESS? Or was there still a reduction in size even with the large bin?
It was, and I should probably defer to Stephen on that one,
Sure.
as the UXO expert on our team. But I believe that is true. We did have different maximum sizes for different parts of the site as well, so it got a little more complicated than that. Stephen, do you have anything more to add?
Yeah, absolutely. So the large size bin was our max MSD for the MRS worked inside of, but on this project, it was slightly unique. We had different exclusion zones set for our different MRSs. So that's why we had in the size bin the inclusion of one of the figures that Craig had shared, the 4.5-inch barrage rocket. So one of our MRSs had a 315-foot exclusion zone. But in short, yes, the MSD for the large size bin was our greatest fragmentation distance in accordance with ESS.
Okay, great. And I see John's camera's still on. He's smiling. He must really like you're really using that conceptual site model to its full benefit there. John actually had a question for you guys. It was difficult to perform AGC at the site. Would you consider the size estimation as a worthwhile activity, specifically thinking of impact to the public in retrospect?
Yeah, Stephen, you're closer to dealing with the public than I was on that one.
Sure, absolutely. So in short, yes. In a longer answer, in the densely populated neighborhoods with an exclusion zone as great as the M45 81 millimeter at 241 feet, the amount of residents that partook in the exercise, we had about 75% in that neighborhood. And the challenge is getting those that did not partake and that are not familiar with the program and what we were doing, making contact with those residents and landowners, but then also trying to coerce them to leave their property for a set amount of time. And then whenever you take into consideration that you may be evacuating 20 to 30 homes in a densely populated neighborhood, if one person doesn't leave, then your entire day is pretty much shot. So in a firm fixed priced world, it definitely behooves the contractor to perform reduction of MSDs and apply this methodology. But it also behooves the government too from a perception perspective.
Great. One last question for the two of you. The 75 millimeter end cap did look like a grenade in the AGC data. How was it viewed from a exclusion zone evacuation perspective? Was it in the small bin?
Greg, I'll let you take the first pass and I'll supplement you.
Yeah, it was in the small bin, and that's why we stopped using the reduced evacuation once that was found, because it was in the small bin, but it was larger in diameter than 60 millimeters. And that's one where I think something that's often difficult for our projects occurred to move past that challenge. And that was getting the geophysicists and the UXO experts all together to talk about it, where the geophysicists who see and have a deep understanding of the AGC results can see that it was the right decision based on those results. And then the UXO experts can understand that, yeah, that it was the size and shape of a small UXO, and therefore it was the right decision. So having everybody come together, I think, was critical for moving past that.
I think maybe to further supplement Craig, that the 75 millimeter cap, while it was greater than the 60 mil in width, it was not greater in all sizes and shape. But also what came away from that is a more stringent awareness or understanding in our SOP through an amendment to count what constitutes an immediate failure and what does not. And then one of the big things that we learned out of that process was that selected TOI, if you have a secondary source that's greater than the size threshold being utilized that was not categorized as TOI that would have been further rejected, but was found through the investigation of the primary TOI, that also wouldn't constitute a failure because it was selected through the of interest for intrusive investigation. It was just subsequently investigated through the process of what was selected as a target of interest.
If you don't mind, Harry, I'll actually supplement both of their answers as well. This was an interesting one. So in most cases, when there's a failure on a project, a root cause analysis is performed, a corrective action is developed, the project team approves it, and they carry on. Due to the element of explosive safety behind this, the policy is in place that both DAGCAP and the Services Explosive Safety Center, whoever that may be for that particular service, needs to review as well. So I was notified of this failure, got to participate with the project team immediately. I don't know if Craig and Stephen know this, but when I saw it initially, I was like, this is the dumbest thing I've ever seen. Like, why are we arguing over this? Obviously, it's small. But I mean, by the letter of the black and white SOP, we had to have the discussion. So they did the right thing. And I think it just gives motivation to having clear, detailed SOPs and explanations for each item. And as Craig said earlier, make sure the geophysicists are talking to the explosive safety experts, because I know some things just enough to be dangerous, but I don't know that this certain item was only used after 1970 and we're on a site that was used in 1940s. So those conversations need to take place and walk through each item one by one.
Sure. We just had another question come in. Oh, John, you're still talking, but you muted yourself, or someone muted you. Well, we have another question for you and for the group at large is how do the local residents feel about AGC clearance versus a metal-free clearance? Many times the perception is that if there's still components present, it's not tolerable to civilians and the public. How did you go about educating clearance to these stakeholders, which is maybe a Stephen question, huh?
Sure, absolutely. I'd say that through your initial contact phase with these landowners, that's your most important phase, because you're setting the tone for all the supplemental conversations that you're going to have with these landowners, and you're building trust, right? We're building a relationship with them. The community is going to talk. They're going to talk to their neighbors, but explaining the process from a high level, and then kind of adapting how you're explaining our phases of work and our process. Based off of a landowner's interest. Some are very interested and some aren't. So kind of adapting that as we go along, but having a general process through coordination. We had a very, very, very stringent process in which we would talk them through each phase of the work, why we're doing it, because on this site, unfortunately, a lot of previous clearance activities have been conducted stemming back to the early 2000s. So for a lot of these landowners, this was clearance number 2, clearance number 3 for what we needed to do. So understanding that what we were going to do and why to limit how much we were going to be impacting them was prudent, but also letting them know that we were going to map the area and then only dig certain targets inside of these densely populated neighborhoods. And some of these houses are worth over $1 million. So you can imagine the level of detail with manicuring of their lawns and such. So it was greatly appreciated. It was welcome. Good question.
Great.
I think programmatically, Stephen gave an excellent answer, but programmatically, it's something we still need to develop answers for. We have amazing 3Rs program, recognize, retreat, report. It works resoundingly well, but it's sort of been straightforward for a number of years now. And I think having some of these conversations of metal isn't necessarily scary, but if it looks like this, it might be scary. We need to communicate those things better to the public, and we're working on it. I don't know if I have the answer now, but hopefully soon.
Sure. Well, and I guess with the physical properties that we're looking for, probably things that look scary are going to be removed in most cases, right?
Ideally, yeah, since the polarizability matching is shape based, most of those items should be removed. So you're absolutely correct in that regard. Some of the landmine conversations we've been having, maybe not. We still got to explore that arena, but for most of our cleanup sites, that is true.
And nice segue there again, John. So that's all the questions we had for you guys. Moving on, Florent, his marine system, I think we had time to answer all the questions that were given for that one as I look through the Q&A here. If anyone has any additional ones, feel free to pop them into the Q&A. Otherwise, we'll move on to Randall. We answered some of the questions for your presentation, but not all of them. A question we had there was for you, Randall, is there a limitation with respect to high frequency sensors and the potential to set off an IED? Oh, it looks like you might have, and I apologize. I see now that you have answered that in the, Randall did answer that in the Q&A here. And he answered the next question as well about external noise sources. All right, well, in that case, that takes us on to Moriyuki Sato's presentation on his dual sensor. Some of those questions we were able to answer, but there were some that we did not have time for. Like with regards to positioning, is that done with RTK GPS? Is there an IMU unit with your system, or I know it's real time, so I don't know if that's necessary.
Yeah, I just want to talk about it that we are also seeking to use RTK GNSS, but in many cases in the humanitarian demining, for example, in Cambodia, it is in a jungle, or in Bosnia-Herzegovina in a forest. And most cases, it is very hard to catch the signal from GNSS. So we do not use it in this moment. If it is an open space, we can use it.
Okay, great. And another question are the limitations of the system.
I do not exactly understand the meaning of the limitation, but one of the limitations is that the accuracy of the positioning. We are using in this moment the accelerometer, and the positioning accuracy in our system would be maybe a few centimeters, or better than a few centimeters, maybe 1 centimeter in a restricted area of the 70 centimeter by 70 centimeter. But if you scan the larger area, unfortunately, the accuracy will be decreased, and then imaging accuracy also decreased. So, in fact, we are planning to improve that accuracy of the positioning, and also we are thinking an alternative way to do that, but it is under development. Okay. I think that's one of the limitations. And also another limitation is that the most of the humanitarian demining by a conventional metal detector is carried out on a flat area. But if it is a slope, typically in a mountainous side, the scanning is a little bit difficult. And then the data quality of the GPL is degraded, and then imaging is not so easy. That will be also the limitation.
Okay, I could see that. You probably want the sensor parallel to the ground surface to couple as well as possible.
Yes, but it is a quite common operation for the metal detector. So I think we do not have to change it so much.
And there was a question about the GPR system. Is this your own system, or?
Yes, basically it is our own system.
Okay, and the EM, is that a single frequency domain?
Yeah, it's a multiple frequency, frequency domain operation and multiple frequency.
Okay. And then I think our last question for you was, does detection require manual inspection of the display for each 70 centimeter by 70 centimeter collection area for the EMI and the GPR?
Yes, in this moment, the miners manually inspect all the images. And as I shown in my slide, the GPL image, the depth can be changed, and the miner will check the shape of the object that appears in the images. But our system acquire the data, and all the data is stored in smartphone. And time to time, for example, in Cambodia, I visited there and downloaded all the data to analyze it. And now we are developing the system to automatically download all the data through the internet. And then if it is achieved, we have so many data sets. And these data sets can be used for the sample data for machine learning. So we have a plan to implement it in an AI system so that it will support the inspection of the miners. But the one reason that we have not to do much on it is that I think in a humanitarian demining, the miners is really rely on the reliability of the metal detectors. And they think that the metal detector response is really the correct. And at first, the GPR will be quite suspicious because it could contain so much clutter. And until they believe that the GPL can really detect a valid object, I think we should leave that final judgment by the miner by themselves, not the automatic detection or the automatic advice from the software. So that's why in this moment we are using the manual inspection by the deminers. But we are planning to implement the AI system in the near future.
Great. I know there's some other presentations involving neural networks, so maybe there's some crossover opportunities there. I think that's the last question I had. I see, Jasper, you turn your camera back on, which I appreciate. I'll hand it off to you now.
Sure. So I see a question. I believe this is for Sophia, and it's asking about what kind of software is needed to acquire the data, your thermal data. Is it possible to acquire data from 4 to 5 meters altitude, and how fast, 4 meters per second? So essentially, what is the resolution? What is the flight height? Potentially, what is the sensor you're using? Is it FLIR or another one?
Yeah, so height of 4 to 5 meters should be possible. It really comes down to the pixels on target. And so if you have a higher resolution camera, then you can get a little higher. So our limitation is more of pixels on target rather than strictly altitude. And we have been using a FLIR long wave IR camera, and we just upgraded, and I forget what our new cameras are, but we're also using Polaris Technologies Pixis polarized long wave IR, which can help with the surface mine detection as well.
Really interesting. I have a follow-up on that. So you said pixels on target. So anti-tank mine, for example, you can have a lower resolution and detect it because it just has larger surface area. So do you have an estimate on the number of pixels that require a unique detection? Obviously 1 pixel is too small because it could just be noise. So what is like the upper and lower bounds on that?
So we've been able to detect for surface mines down to like a 8x8 pixel bounding box. That's kind of the lower limit. The buried objects, we need a little bit more pixels on target, like maybe I think the lowest has been like 12x12 pixels. Obviously more is better, but yeah.
Excellent. I think there's another question for you as well. This is on regarding the environmental knowledge, which influences thermal imagery. Is there an ideal time of day to conduct the survey?
So the kind of thermal crossover times of day are best when the sun's rising, things are heating up, and then also sunset and into the night, especially if there's a lot of solar loading. If it's kind of warmer weather, then the differential cooling rates of the soil and the mines can give you good visibility well into the overnight hours. And there are certain times, like maybe there's in the middle of the day, a strong cold front comes through, and then you get like super great visibility, or it's been really cloudy and then the sun comes out. So it's also a little bit more complex, but in general, those thermal crossover times are best.
So with the those thermal crossover times and higher differentials, you get better, essentially better detections for your thermal imagery. A follow-up is, does that also increase the false positive rate? Because now there's, every rock in the field is also being subject to this higher differential. And can you sort of utilize both times of imagery to improve false positives or reduce them?
So we currently don't do that for the like warfighter support application, but leveraging a like time series of imaging would be really help with that problem. But currently we don't implement that, but that is something that would definitely help it.
Yeah, and I understand you probably have to, with stealth and everything, you just have to go fast and quick, collect one data set and analyze it. So in regards to that, have you field tested this system in Ukraine? Like what stage of development is this in? If you can speak on that.
So it's a lower TRL level. But so we haven't gone out into the field and like in Ukraine to test it, but we're part of a research program that is doing field collection events in all sorts of representative environments, and to kind of evaluate the current sensor and algorithm performance. But we have not been to actual regions of interest like Ukraine.
Understood. Do you have any, based on that data you've been collecting, has the algorithm performed better in certain environments? Can you speak on that?
Yeah. So we have had some challenge when there is a lot of vegetation on the surface, because that leads to a lot of thermal noise. And but we have some recent work. I presented it at SBIE last week, so if I have a paper on it if that's of interest, where we modified some of the approaches that I talked about today to handle that background noise a little bit better and tease out our targets from that noisier thermal background. And we're able to infer on a completely new climate type based off of our training information.
Interesting. And this is probably a question a lot of us struggle with in developing technology for explosive remains of war detection, landmine detection, is where do you determine that threshold when, when you're tuning your algorithms for false positive rate? And this is something that I have to consider a lot too, is what is you don't want to have a million false positives for one detection, but you also, that missing a detection is much more dangerous then. So how do you tune that, and what's your decision making there? I know the military space is a bit different than humanitarian mine action, which has higher clearance acceptance rates.
Yeah, that's a great question. And so we kind of handle that problem by, in our first step, allowing a lot more false alarms than what would be acceptable anywhere. And then we can get much higher accuracy by doing the second classification step, versus a lot of folks use those kind of fancy one-step YOLO type detectors, but you can get better performance when you have that two-step, where you can get all possible detections, but you have to make sure you're not overwhelmed and detecting like the whole image. And so that's something that was addressed in that SPIE paper I discussed a moment ago.
Great, thank you so much for all of that. And I have a lot more questions, but I'll spare everyone else. So another question for Davrin on your system. So can the tracker, we saw that there was a tracker device that, helps with the location of the sensor. How far does that need to be from the operator? Is it sort of something that you walk with and place as you're doing your line, or is it something you leave at your base camp?
Yeah, I mean, what we were looking for is to have something that the miner would normally have to be able to carry and work with the normal length width of the mining lane. So if you have a lane that's like 1 meter wide, then you would ideally have a small lightweight stick to put in front of you, and you can sweep a detector in a normal way. It's normally done in standard operating procedures. So our first, the wooden thing that you saw in the presentation, it was able to cover an area of, let's say, 70 centimeters by 70 centimeters. Now with our next generation, we are able to go a bit more with in terms of width, so we can safely cover a whole meter, leftwise and rightwise from the stick. And a detector can be moved, let's say, at about up to some 80 centimeters from stick. So we think this is like a normal area that an average miner could cover with a normal sweeping pattern. So yeah, hope that answers the question.
Yeah, and I have a technical question on training your machine learning data set. So you showed a very, few different kinds of landmines. When you're training the data set, how specific do you make it, and how generalized, right? If, let's say you have a class for 60 millimeter mortars, or are you saying PMA 2 class, PMA 1 class, things like that? And, how do you, I guess, what's the specificity of it? Is it just an anti-personnel mine, or is it caliber, things like that?
Well, that's a great question. Well, right now we've been pretty much limited by the size of our let's say data set and the size of the objects that we were working on. So we only had a few types of landmine surrogates, and so we pretty much generated some clutter items by ourselves. So we played a bit with different classification approaches. So the thing that shows great promise, at least by now, is using the convolutional neural networks. And we actually been able to let's say identify. So we played with different classification approaches. So one approach is clearly the binary classification. So is it something dangerous or not dangerous? And especially if you're doing something if you're targeting the humanitarian, the mining industry, then we think that the classification approach should be somehow biased towards safety. So it's better to declare, if you're not sure, it's better to declare something that it's mine than it's clutter. Then so yeah, we've been doing lately this kind of binary classification approach and introducing some kind of, let's say, safety biases in the whole classification algorithm. But again, we need definitely we need more data. We need more data sets and more experimentation. Without that, it's just not going to work.
Understood. And in terms of the sensor, actually the data output, I saw some really interesting visualizations on essentially estimating the shape and positionality of the item.
Mhm.
Can you speak on that, sort of what that, the visualization of it for the user, as well as estimating depth and how accurate that is, and where you're planning to go with that?
Yep. Well, I mean, when we just started with the whole approach, we didn't start first with doing the whole machine learning classification part. So our main goal was, okay, let's see if we can actually utilize the EMI data from the detector and the positioning system to get some really reliable signature. And so what are the signatures? We're actually doing quite very similar thing as all the colleagues from the UXO the sector. And so we're actually estimating some dipole moment parameters and polarizabilities, and then from those polarizability curves, we are then trying to see you can then estimate the shape, the size, and get a better look into what kind of an object you're dealing with. So this was our initial assumption, and it turned out that we are actually able to, for those sets of targets that we played with, we were actually able to get pretty good signatures. So we can be pretty sure that we detected, let's say, a small aluminum cylinder at 10 centimeters. So our whole system is actually, of course, it's limited by the size of a metal detector. So you use a typical metal detector with a search head of 20 centimeters diameter. So it can cover up to some 20 centimeters, let's say, roughly, depth range. And it works quite well for let's say, those types of targets. So if you're looking for something, let's say, smaller, like, anti-personnel landmines, small submunitions, something not that big that will saturate your amplifiers, then it works quite well. And the modeling that we are using, the dipole modeling, it actually seems to be also a quite good fit. We also found out that the positioning accuracy, let's say the localization accuracy, affects quite a lot your signature extraction process. So if you're able to localize the target quite accurately, then you'll be able to also get its signature quite well. That this is the part where this is due to the physics, because all those parameters are coupled together in the response. So you have to make sure that you really do your localization quite well to be able to get those signatures also well. And what was encouraging with our system is that so we are using a commercial metal detector, so you can use it just as a basic metal detector, see how that works. And we're also using the same detector, let's say, in this kind of more smarter mode, where we use the raw signals in our own software and everything, so we can compare the two systems. And what was encouraging is that so if a metal detector working as a metal detector was able to detect something at 15 centimeters or 10 centimeters, we were able to identify the same target almost at the same depth. So that means that we are pretty much at the far level of the technology. So we're using the signals as much as we can. So this was really encouraging. And of course, it would be interesting to also explore this research to other types of targets. But of course, we will probably have to maybe use a different tool, maybe a larger detector with larger cost to play with larger targets. And because of course there's no silver bullet detector for all kinds of tasks. You cannot use a single device for anything. It's just the way it is.
Yeah, and there's a question from Dante to you. Could you discuss more about your method of soil compensation and what difficulties you have run into?
Yeah, I mean, you've seen in one of the slides of the presentation, what the real issue is that the signal from the soil actually can be 1 to 2 orders of magnitude larger than the signal coming from your target. So this is especially true if you're trying to detect something really small, like a anti-personnel landmine in red soil. Then this is really hard stuff. So even if there are multiple difficulties with this. So first of all is the question of the liftoff. So that when the miner is working above a target, it's impossible to keep the search head almost parallel to the ground. So you always do some kind of small liftoff variations, and this will create a large signal that is sometimes very difficult to separate from the actual target signal. That's one issue. The second issue is that the soil is not perfectly flat. So for larger targets buried at greater depths, this is probably not an issue. But if you're looking for something small, buried up to a few centimeters below ground, then the soil roughness affects everything. So this is why we actually decided to use the positioning and to actually try to map the soil. So this is what we're doing. We're actually at the same time trying to detect something and map the soil, and hopefully by mapping the soil, we will be able to separate those two signals. And at this point, it seems to work. It's better than we expected. So this is encouraging, and we just need to move on and see how it works with other types of objects.
Thank you, Devon. Is there any other questions from the crowd related to this talk, or other ones? If not, I have some more questions. I guess I have a question for Craig. Everyone else, we have around 15 more minutes, and if we want to end early, that's also great. For you, Craig, this seems, and modeling, Old Moslow's a huge task. Is this something that your team is planning on doing in other regions as well, and applying this methodology of structure from ocean photogrammetry for large-scale planning and assessment?
We've rolled it out in other regions of Iraq already. So we were operational in Anbar. We did it for the railway stations down there to justify clearance and the rebuild. And we're currently running it through 3 villages in Kirkuk. We're now operational in Ukraine as well. So the guys are starting to process large sites, but our operations have slowed down over there for the time.
Sure. Well, it was a pleasure to co-chair on today with Harry. There's a lot of really interesting technology. I'm really excited for the applications both in UXO realm as well as landmines and HMA. So nothing else from me. I'll let everyone, regardless of your time zones, get back to lunch, dinner, breakfast, or sleep.